Hello, this is Jason Kendall, and I'd like to welcome you to my introductory astronomy lectures. You're about to begin a wonderful journey with your start in the hobby of amateur astronomy. There are fewer more enjoyable activities than just going outside to see the night sky. You'll see the stars rise and set as they move slowly across the sky. Perhaps you'll see a shooting star, perhaps you'll enjoy the moon in one of its many phases. Perhaps you'll be so fortunate as to see a comet. To enjoy this hobby, you don't need a telescope, you don't need a camera, you just need time and a dark sight. Go to the darkest place you can find where you can see a lot of stars and just begin looking. That's the basics of observational astronomy. Get away from all the bright city lights as far as you can so you can see pictures like this. These are the stars from Boulder, Colorado. I took this 60-second exposure using a DSLR camera on August 16, 2017 at about 11 p.m. from the mountains above Boulder, Colorado. Boulder is the sky glow off to the left. The little dots across the horizon are a couple of planes flying near Boulder International Airport. We can also see, in addition to the tree in the foreground, some people's houses in the background. More prominently, we see the Milky Way centered up, rising from the horizon. That's not smoke, that is the Milky Way. Very often when people first see the Milky Way, they think it's smoke, especially people who've lived in cities their entire lives. They just can't believe it when they see the Milky Way in the sky in a very dark location. But if you also go outside on such a dark night, and you can find a place that's hopefully nearby, you'll see it too. You'll also notice that you get lost trying to count the stars. This image alludes that if you scanned around the sky in a truly dark place, you would probably find that you'd see 2,000 to 4,000 stars. Most places are blighted by urban light pollution these days, but you can still find several places if you go hunting for them, and I suggest you try. Navigating around this image, just behind the trees, is the teapot shape of Sagittarius, and off to the right, the bright star above, straight up from the hill. It looks kind of reddish in between the stars that are bluish on either side. That's Antares, the heart of Scorpius. The pincers of the scorpion are almost to the edge of the screen off to the bottom right. If you look at the two lights that are close together on the horizon, those two almost bright yellow lights, and then if you look straight up from them, you see what looks like one of the brightest things in this picture. That's not a plane. That's the planet Saturn in the constellation of Ophiuchus, which lies just between Sagittarius and Scorpius. When we look out into the night sky, we can certainly see quite a few things. Now, how would I exactly point out to you which thing Saturn is in the sky? How could I be certain that you're seeing it, or Antares? To help us communicate, we have two things to use: how high it is off the horizon and where it is along the horizon. This forms the basis of what we call the horizontal or altitude-azimuth coordinate system. Now, if I mark Saturn with this green bar to show its altitude of the horizon, we have the first of our needed measurements. We can ask, why does the bottom tick mark, which should be the horizon, go below those hills? One might think that the horizon should be at the top of the hills, but it's not. Perhaps a better way to think about it is the horizon can be defined to be 90 degrees down from straight overhead. That overhead point is called the zenith. So if you measure down from the zenith to the hilltops, that'll be less than 90 degrees. I've also marked south. That means due north is directly behind the viewer in this picture. We could measure angles from the south that are marked along the horizon, but we choose north instead, due to the ease of finding the North Star. Therefore, we can say, what is the angular measurement along the horizon from due north to the bottom tick mark of the line below Saturn? Well, we need to choose a direction. The direction we'll choose is north to east to south to west, then back to north, or clockwise as seen from above. In this image, we'd measure from the tick to the left until we got to due north. Given the date, time, and location on Earth, this works out to be roughly 210 degrees. We call this angle azimuth. We could also measure that Saturn is 69 degrees down from the zenith, which means it has an altitude of 21 degrees off the horizon. It's important to note that the altitude and azimuth angles of almost everything in the sky are always changing and are always different for different observers on the Earth. And lastly, they're never the same from one night to the next. However, there are two notable exceptions, and I'll let you ponder that. Another name for altitude and azimuth is the horizontal coordinate system. Now let's define the horizontal coordinate system properly. We can imagine the sky as being a dome overhead, with the horizon all around us. We then find north using a compass, or much better using the North Star. Now we're ready. We need to have a good way of measuring angles too, but let's leave that aside for the moment. To find the coordinates of some star in the horizontal system, we measure the angle from north towards the east, i.e. clockwise looking down from above, until we get to the point on the horizon directly below that star. That'll be our azimuth angle. Next, we measure the star's altitude up from the horizon, or if you wish, 90 degrees minus the angle between the star and the zenith. In the diagram, the azimuth is less than 90 degrees, because it looks like we didn't even get to due east. Let's call it 60 degrees, just to assign some reasonable number to guess with it. Likewise, the altitude looks to be maybe 50 or 60 degrees. You might ask why we even have or even need this coordinate system. Perhaps you found a comet and wish to tell some friends nearby on the phone where to look in the sky. So long as they were not too far away from you, this should work pretty well. If they're hundreds of kilometers away, then it won't work, and we'll need a better way of telling distant friends who will try to look for it tomorrow night. A good way to think of alt-az, as horizontal coordinates are known in shorthand, is to call them local observatory coordinates. They're important to you at your observing site because when things are low in the sky, i.e. a small altitude, there's lots of atmosphere between you and space, so things are dimmer close to the horizon. You might find that you want to observe things that are at least 30 degrees above the horizon. Why? Maybe the observatory has a big tree that was planted by the founder decades ago, and the board of the observatory's location has decreed that the tree cannot be cut down for your use with stargazing. Therefore, you have to plant around the tree. While this may sound silly, there are examples throughout amateur astronomy where you need to wait until the object gets much higher in the sky before you can observe. It's mostly the case that the atmosphere dims, blurs, and reddens low-altitude objects. In general, we like observing things as high in the sky as we can. This goes by way of saying that when planning observing runs as an astronomical observatory, you always want to optimize your viewing for your location. Again, the alt-az of a star, comet, or planet in the sky constantly changes and isn't the same for different observers at different locations on the Earth. Let's now put the idea of the horizontal coordinate system into practice. Running in the background is Stellarium, which is a free sky simulation software. We're going to look at the azimuth and altitude of various stars. These are the stars at a given place, the place of the observer, somewhere on Earth. What we see across the bottom of the screen is the horizon. The horizon is demarked by various little red letters. The capital letter E denotes east, SE denotes southeast, and northeast is denoted by NE. From the date time clock in the upper right, we see that it's somewhere in December 2034. We also see that the time is speeded up and the stars are moving fast. The numbers in the clock that are scrolling by quickly are hours, minutes, and seconds. It's set to run at approximately 10 minutes per second. I've also turned off the atmosphere so we don't get the glare of the sun. I'm doing this, of course, because I want to focus on the positions of the stars in the sky and how they change with time. The current location is New York City. We'll change that location around shortly. You can see the location in the lower left. Now let's focus on a couple of stars in the sky. The current time is about 7 p.m., and I'm going to pause the time and take a look. As you can see, there are labeled stars rising in the east. Let's use Beta Taurus. Now, I'm going to turn on our angle measurement to see how high off the horizon Beta Taurus is. I'm going to place one end of it on the star and bring the other end of it all the way down, straight down to the horizon. We don't want to go side to side, just straight down. It says it's about 48 degrees in altitude, and that's a good first rough estimate. Now let's turn that off and click on the star itself. We see that Beta Taurus, which has a proper name of Elnath, has a current altitude of about 47 degrees and 56 minutes, almost 48 degrees. That's very close to the rough estimate that I used with the angular measurement bar. In the upper left, Stellarium is telling us that Elnath is 48 degrees off the horizon. And its azimuth angle is 90 degrees, and that's because it's almost due east. Let's stick with Elnath for just a minute. Now, what I'm going to do is I'm going to bring up the location window on Earth, and you can see on that map a red arrow pointing roughly at New York City. Let's now change the location by changing only the longitude and go straight west. We go over the Midwest and end up in the mountain states, and let's pause here. We're now maybe over Colorado or Utah. That seems to be good. Let's put Salt Lake City into the search and see that location. Hey, I was pretty close. So we have a marker on Salt Lake City, Utah. Oh, and by the way, the Greek letter and the abbreviation is the Bayer designation for a star, typically for the bright ones. Elnath is its common name, but its Bayer designation is Beta Taurus. Here, in Utah, it has an azimuth angle of 69 degrees, so that's north of east. It also has an altitude of 20 degrees. So this is why you can't tell someone over the phone who is at a distant location on Earth to go outside and look for a star at the altitude and azimuth that you measure locally. To further demonstrate, let's just go way far north. We're just going to increase the latitude. Let's end up in northern Canada, the Great White North, and warm up with some Tim Hortons. We'll see that the star's location didn't change much. It did change the azimuth angle a bit, and it changed the altitude a bit. But now, if we scoot back over north of New York City and see it from that location, see how the star's positions change as we careen around North America? Now, if we observe it from western Greenland, the azimuth angle is 140 degrees and the altitude is 47 degrees. If then we jump to somewhere in Brazil, that's way over there. It's 38 degrees above the horizon, and its azimuth angle is 34 degrees. It's in somewhere in the northeastern part of the Brazil sky. So okay, let's go over to Western Europe. Where the heck is it? It's somewhere else now. We'd have to probably swing farther around to find it in the sky. As you can see, for different locations on the Earth, for the exact same time, the position of the star in the sky changes. Let's go back to our original location, New York City, still looking at Beta Taurus. On this date, December 6th, 2034, at 2100 hours, that's roughly where it would be in the sky. Let's get rid of this location window and we're going to speed up time again. Now let's look to the south. We see the constellation Orion with some familiar stars. They're floating east to west. If we look to the west, we see things setting, which means their altitudes are decreasing. Stars ascend in the east and descend in the west and go laterally across east to west along the south. Now we finally look north. I want you to note there's one little star about which everything seems to be rotating. All the stars seem to go around Alpha UMI. That's Polaris, the pole star. It has an azimuth angle of roughly 0 degrees and an altitude of 40 degrees. The altitude of the North Star, or Polaris, is a great measure of your latitude. Your latitude on the surface of the Earth is determined historically and very reliably by the location of the North Celestial Pole off the horizon. For New York City observers, that star is approximately 40 degrees off the horizon. Now, if we move further and further north, we see that Polaris goes way up in the sky. If we go up to, say, 70 degrees north latitude, we're far north, but not yet at the North Pole. If we want to see what that looks like, let's zoom out just a little bit more, and now let's keep going north until we get to 90 degrees north latitude. When Polaris is at the zenith, you are at the North Pole. The zenith is where all the lines of azimuth converge, and about which all circles of altitude are centered. The zenith is simply the point that's straight overhead. Polaris is important because it is located in the sky next to the North Celestial Pole, which is the place in the sky that all stars revolve around. Suppose we go further south, down to, say, 10 degrees north latitude. If you're at 10 degrees north latitude, you're somewhere right above South America. And if we go to, say, Quito, Ecuador, which is on the equator, here the north celestial pole is exactly on the horizon at 0 degrees altitude. If we then go south of that, Polaris is now below the horizon. So now what do? You can't measure your latitude that way. Now let's swing all the way around and look due south. Now we find there's a different location in the sky that stars seem to be rotating around. That's called the South Celestial Pole, and here the altitude of the South Celestial Pole is your latitude in the southern hemisphere. We see that there are no bright stars that are associated with the South Celestial Pole, however. That's sad, because it makes it difficult to find out how to find our latitude. However, there are some tricks. You can use the Southern Cross, which is an asterism that points roughly at the South Celestial Pole. More on that another time. Let's go back to New York City, but we're still looking south. So there's Orion once again coming across. Let's just stop time once more and say, what is the altitude of, say, Rigel right here off the horizon? I'm going to get that angle measurement again to solidify the idea. The altitude of Beta Orionis, or Rigel, is approximately 39 degrees off the horizon. It has an azimuth degree of 160 degrees and an altitude as roughly measured of 39. As you've picked up by now, the horizontal coordinate system is only suitable for local observers. It isn't a coordinate system that we can use to communicate locations on the sky between people that are separated by any great distance on Earth. Next time, we'll look at the first attempts to help people communicate locations in the sky, and they did that with constellations. Last time we looked at one way of locating things in the sky, the horizontal coordinate system. How might we organize what we see up in the sky in general? To help, I've taken some snapshots with an observatory simulation program called Stellarium. At first glance, we see a bunch of stars in the sky. You might recognize the Belt of Orion, the Head of Taurus, and the Seven Sisters, otherwise named the Pleiades. However, how would you point that out to someone who's never looked up at the night sky before? You might just wing it and say, see those bright stars in the slightly diagonal line near the horizon? That's the Belt of Orion. Now the belt is surrounded by 4 stars that make up a rectangle. Those are the shoulders and feet of Orion. Orion also has a sword on his belt hanging down. That's a good start. What we've described is called a constellation. A constellation is just a pattern of stars in the sky. The stars don't have to be related to each other, and in the vast majority of cases, the stars that we use to denote a constellation are not at all related. If we look up to the right from the right shoulder of Orion, we see the V of Taurus the Bull. One of the horns of the bull has a bright red star. This is one of these cases where the prominent stars of a constellation are certainly related to each other. These are the brightest stars of a star cluster called the Hyades. Further up and to the right, we see the Pleiades, otherwise named the Seven Sisters. This is a real cluster of stars, and because the cluster's appearance looks like a tiny cup with a handle, we call its readily identifiable shape an asterism. The Belt of Orion is an asterism. The V of Taurus is both part of a constellation and an asterism. Asterisms can span across many constellations, or they can be so small as to need a telescope to see them. Again, both constellations and asterisms are named patterns of stars in the sky that do not have to be related to each other. All constellations and asterisms are products of our place in space. If we went 1,000 light years away from here, we'd not be able to pick out any of the familiar shapes, except possibly those that are directly behind us, and even those would be heavily distorted. I've just now added the artwork associated with these various constellations. This artwork is based on Western mythologies. A lost work of Hesiod's, known by the summary done by Eratosthenes, said that Orion was the son of the sea god Poseidon and Euryale, daughter of Minos, king of Crete. One day, Orion was hunting on the island of Crete with the goddess Artemis. During the hunt, for some reason, Orion threatened to kill every beast on Earth. Gaia was horrified, and sent a giant scorpion to kill Orion. The creature succeeded in its mission, and after his death, the goddesses asked Zeus to place Orion among the constellations. Zeus consented, and as a memorial to the hero's death, added the scorpion to the heavens as well as the constellation Scorpius. Orion as a constellation seems to be hunting Taurus the bull, and he's seemingly backed up by the unicorn Monoceros. He's followed by his dog in the lower left, highlighted by Sirius, the dog star. The dog, Canis Major, seems to be chasing the rabbit at his feet. There are all these kinds of little stories you can tell by imagining that these dogs and heroes and animals are up in the sky. Many other cultures also called Orion a great hunter or giant. Notably, the Babylonians called Orion the true shepherd of Anu in cuneiform tablets dating back to about 3000 BC. The ancient Egyptians from about the 23rd or 24th century BCE called Orion Sa, a god, whose form Pharaoh would take when he ascended to the heavens. The list goes on, but the current star names of Orion hail from medieval Muslim astronomy. That there are stories and myths and legends placed upon the patterns of stars in the sky says so much about humanity's need to connect to the everlasting and unchanging. It is easily argued that religious thought has its roots in noting the permanence of the stars' patterns year after year compared with the frighteningly temporal nature of life on Earth. It's also a personal belief of mine that as we lose our dark skies to light pollution, we lose a significant part of what it means to be human. We lose our sense of things bigger than ourselves, and we lose our connection to the journey that is represented by watching the sunset. The slowly appearing stars in the darkening sky arise to tell their stories and remind us of ancient times and times that will be. As the sun rises, this alternate reality recedes into the realm of dreams. The striking difference between day and night calls for us to create these stories and learn from them. To help us understand the ancient stories better, I've traced the constellations with lines that denote the most prominent asterisms. This connect the dots game helps us better see the patterns. I've also added the constellations' names. Now I've added some names for some of the brightest stars. Aldebaran is the name of the eye of the bull. Betelgeuse is the upper left shoulder, as we see it, of Orion. On the right is Bellatrix, the advancing foot is named Rigel, the knee he's resting on is Saiph, and the belt stars are named Al-Natak, Al-Nalam, and Mintaka. You can see Sirius in the lower left and Procyon and Canis Minor in the upper left. Most bright stars are named. Many have Arabic names, which have been formally adopted by the International Astronomical Union. This is partly in honor of the fact that Muslim astronomers kept the knowledge of ancient Greek astronomy alive in the European Dark Ages by translating Ptolemy's Syntaxis Mathematica into Arabic as the Almagest. Later translations, hundreds of years later back from the Arabic, allowed Western astronomers the opportunity to use improved measurements of the positions of stars and planets to eventually prove that the Earth orbited the Sun. Aldebaran's name came from the Arabic al-Dabaran, meaning the follower, because it seems to follow the Pleiades. The name Betelgeuse was derived from the Arabic Yad al-Jawza, the hand of Al-Jawza, i.e. Orion. An error in the 13th century reading of the Arabic initial Ya as Ba eventually led to the European name. Sirius hails from ancient Greek, which translates into the Scorcher. We could go on, and I suggest you look up the star names on Wikipedia. Little tidbits are really interesting. Many traditional names have been used for centuries across cultures. It seems that the sky is a great meeting ground for people. I've removed the art so we can just show the lines and some star names. It's fun to draw them out for a friend when you're at an evening stargazing session. Might go a little like this. Do you see the belt stars of Orion? They're the three in a row close together, all the same brightness. Good. Now from the leftmost one of the belt, go straight up 12 o'clock to the bright red star. That's Betelgeuse. About the belt's width to the right at 4 o'clock from Betelgeuse is a bluish star. That's Bellatrix. Those two stars are the shoulders of Orion the Hunter. If you look in between those stars and a bit up, you see a brightish star that's not as bright as Bellatrix, but is the third brightest right around there. That's Mysa, the shining one in Arabic. And that's the head of Orion. So let's go now back to the belt. The belt has something right below it, the sword of Orion. The middle star in the sword is pretty fuzzy and doesn't quite look like a star. That's the distant star-forming region called M42, or the Great Nebula in Orion. If we go just down to the right from the sword, we see a bright star, almost as bright as Betelgeuse, but it's blue. That star is Rigel, on the left foot of Orion. We're assuming he's facing towards us, so that'll be his left foot. His right foot is named Saiph, which is interesting because Saiph in Arabic means sword. Swords get moved around, I guess. It's chats like these that happen at every star party across the planet as people teach others the names and traditions of the sky. However, such stars don't help us with the myriad of other stars in the sky, so what's their story? In 1922, at the request of the IAU during its very first session, Henry Norris Russell produced a list of 88 constellations. But these constellations didn't have clear borders between them. Then, in the next IAU session in 1928, Belgian astronomer Eugene Delporte drew up a definitive list of boundaries for the 88 constellations. He used vertical and horizontal lines of right ascension and declination to cover the entire celestial sphere. These modern constellations usually share the names of their Greek and Roman predecessors, such as Orion and Taurus. Those boundaries are what you see as the dim red lines in this image. Any star, planet, or nebula that is in that area of the sky is, by definition, in that constellation. So now it's not just the lines and asterisms, it's everything inside the red boundaries. Let's now take a look at one of those star charts from the International Astronomical Union. As you can see from the website on the left, this is where you can look at all the official ones. This particular star chart is published by Sky and Telescope and on behalf of the IAU. And what we see on the boundaries are, of course, across the bottom and top, you have the right ascension, which is the boundaries that are vertical, and we have the declination, which is the horizontal boundaries. The declination is given in tens of degrees, and the right ascension is given hours. So what we see is the boundary of Orion going around. It's bordered in white. It has the familiar asterisms in it, as well as numerous stars. What's a little different about this star chart that you might notice is across the bottom, the magnitudes are defined. A star's magnitude is how bright it is. So 0 magnitude is like the second one from the left. The brightest star is -2 magnitude, which would be pretty bright. Sirius is the brightest star in the sky, so it lies just between -1 and -2 magnitude. The faintest stars are magnitude 6 that you can see with your naked eye in a very dark location. So this star chart reveals only those stars down to roughly magnitude 6 on the chart. We see there's also proper names on there. We see the green lines that demark the asterism. We also see Greek letters, which are the Bayer designations. And sometimes we have a number by it. So it's like Omicron 1 and Omicron 2, or Pi 1, Pi 2, Pi 3, Pi 4, Pi 5, and Pi 6. But we also have little squares, which are nebulae and so forth. And as you see in this zoomed in view, there's the names of the stars. Betelgeuse has a secondary ring on it, which means that it's a variable star. And we also see some yellow little fuzzy patches. Those things are clusters of stars as well. Essentially, all the major things that you might want to do are typically located on such star charts. As well, professional astronomers use these star charts too, just to make sure they know where they are in the sky. And now I'm just going to show you an example from a different pair of constellations, Ursa Major and Ursa Minor. These are very familiar constellations in the sky, notably the Big Dipper and the Little Dipper. And the Big Dipper is highlighted by called Ursa Major, which is the Big Bear, and the Little Dipper is the Little Bear. And if we zoom out and look at them in the larger size scales in the sky, we can see how these constellations relate to the stars around them. So let's use Ursa Major to help us summarize this entire set of ideas we've been talking about. Ursa Major is the name of the constellation. The familiar asterism is the Big Dipper, and you can kind of see it highlighted with the bolder green lines. The rest of the traditional constellation is highlighted by the green lines, which are dimmer than the main asterism lines. But the IAU accepted boundaries for the entire constellation are the vertical and horizontal lines that ride along the right ascension and declination lines. Those are the official boundary for the constellation. The constellation is, of course, filled with stars, and it looks like we've got some new things in there. There are galaxies, M101 the Pinwheel, and the interacting pair M81 and M82, as well as the planetary nebula M97. So these are some of the major objects in Ursa Major. that can be seen down to, say, roughly magnitude 6 or 7 or so. M80, 182, and 101 and 97 are dimmer than magnitude 6, but we put them on there because they're relatively famous things to go try to find in a small telescope. Speaking of which, what are some free resources that you can use to have star charts so you can go outside and look for things in the sky? Well, a good place to start are the monthly maps that are provided by NASA's Jet Propulsion Laboratory through their Night Sky Network. These maps are created by the Astronomical League, and you can go get them at this website that's shown here. What you get in this thing is a full sky map that shows all the way around, where you're assuming that you're kind of lying on your back, looking straight up at the zenith, and with your feet pointed towards the south. In this map, we can see where Orion is, we can see where the Big Dipper is, there's a bunch of other asterisms out there, and there's other things that you can go poke around and look for. In fact, this is a great way to begin, and it's probably your best start to go out with naked eye observing, just going outside and seeing what's up in the sky and taking a piece of paper with you. Don't take your phone, because your phone will give you night blindness, and you won't be able to see the stars if you look at the bright light coming out of your phone. All right, so there's a bit about constellations and asterisms. Keep looking up in the sky. Now we're going to look at the positions of stars on the sky. We're going to look at angular separation, and we're going to look at a new coordinate system, the equatorial coordinate system, that helps us navigate on the celestial sphere. So let's start with this obvious picture of the night sky. This was done with a 10-second exposure with a DSLR camera on a tripod. And what we see is way off in the distance, mountains covered with snow and trees and things. So we know we're in a very dark location because it doesn't look like there's any ambient light. Notice above we see stars, and it's kind of supremely obvious to state, but the stars are in different places on the sky. And the way we distinguish one place from another is not with a physical distance between left and right on the sky. We're pretending for now that the stars are printed on a dome on the sky. And so they stay fixed on this dome on the sky, and that's not a terrible way of thinking for this purpose. In fact, it's extremely useful. We know that the stars are not fixed on the dome on the sky, but it's useful for this purpose. And this is the basic concept of the celestial sphere. We need to remember that we're not using a yardstick or a tape measure to measure angular separation. We're simply looking at directions, and we're saying we're going to make some kind of way of devising a direction on the sky. Also, obviously, we don't see the stars move with respect to each other night after night. They rise and set, maintaining the same patterns on the sky. So therefore, they're pretty reliable. Now we're going to do two things. We're going to learn how to measure angles on the sky, and we're going to find a good way to map them with a fixed coordinate system. Our next step is to look at the angular separation on the sky, and if we have two directions, say direction X and direction Y, and you're looking at them, it doesn't matter how far a star is away on X or how far a star is away on Y. Now they could be very far away or they could be very near. It doesn't matter. We don't care about the distance to the object for angular separation. We only care that we're looking in one direction or another. And it is that angular separation that defines what we're talking about. So this angular separation is only on the sky and has nothing to do with the physical distance from any of these objects. Next, we can define angular measurement using a very simple tool, our hand. So if you take your hand and arm's length and make a fist, and you put your right hand of your fist at arm's length and close one eye and hold it up on a dark night where you can see many stars, and put one star on the right hand side of your fist and one star on the left hand side of your fist, those stars will be roughly 10 degrees apart. Also, you can use the 10-degree idea to start by the same thing, look straight up towards the zenith, hold your fist out and then put your thumb side of your fist at arm's length straight up, and then it will take only 9 fists to get to the horizon. That's because the altitude of the zenith is 90 degrees. So it will take 9 fists to come all the way to the horizon. For smaller angular measurements, we can use our pinky held at arm's length, and you close one eye, hold your pinky at arm's length, and if there are 2 stars, one on your right-hand side of your pinky and one on your left-hand side of your pinky, then they're separated by about a degree. Again, your hand can act as a 10-degree thing for a fist. Your little finger is about 1 degree across. And for those inclined to use a piano, an open octave, which is separate your thumb and pinky as far apart as you can, and then put those against the sky. Your pinky pointed far out to, let's say you're right-handed, and you point your right pinky all the way out, and your left and your thumb all the way to the left, and separate them as much as you can. And that is about 15 degrees if you hold your hand at arm's length and close one eye. Now we can make very small angular measurements, but let's say you take your pinky and hold it out at arm's length. Guess what? Since your pinky is about a degree, the sun and the moon both are only about half the size of your pinky held at arm's length. They're like almost exactly the same size. And that's why we can have total solar eclipses. Anyway, let's go on. Angular measurement can then be broken down into smaller and smaller increments. We all know that there's 360 degrees in a circle, and therefore there are 36 fists all the way around a circle held at arm's length. You could just use your arm back and forth all the way around. Now we can also then say, we can look at each pinky is a degree. So one of those degrees is going to be 360 pinkies all the way around held at arm's length. We can now divide those things up into smaller and smaller angles. And we do this because there are things that are very separated by very small angles in the sky. Now imagine that you took your finger, your pinky, held at arm's length, and demark 60 little tick marks from the left side to the right side across your pinky nail, and then held that out at arm's length and close one eye and look at that, and those 60 evenly made markings across your pinky, each would be 1 arc minute. So there are 60 arc minutes in a degree. And that's a very tiny angular measurement, and that's why it's actually, we call it an arc minute, because it is an extremely minute measurement. And you could, in theory, have each of those 60 tick marks that you had your cosmetologist paint very carefully on your pinky nail with a very fine toothed, I guess, one camel hair brush or something like that, a very fine brush with one hair. And then you put 60 tick marks in between each of those tick marks on your pinky. So now you have 3,600 tick marks across your pinky. Each one of those tick marks across your pinky would be 1 arc second. That is an incredibly small angular measurement. So there are 360 degrees in a circle, there are 60 arc minutes in a degree, and there are 60 arc seconds in an arc minute. So there are 3,600 arc seconds in every degree. So a second, an arc second, would be the second minute portion. So it is a second order minute thing. So these are really tiny angular measurements. If you do manage to get a cosmetologist to do that on your pinky, you better give that person a really big tip. So the angular size of some object actually depends upon its physical size and how far it is away. Because if something's really near and it's very small, then it'll look big. But if something's really big and really far, it'll look small. When I say look small, I mean its angular size is small. Next, we can then pretend that all of the stars, we can pretend, and this is a really big pretend, that all the stars are on this dome that we're going to call the celestial sphere. And that is a very interesting thing to say, because now we're making up anything, a celestial sphere that is around to which the stars appear to be fixed. And I want to be really clear, there is no such thing as the celestial sphere. It's a made-up thing that's been with us since really ancient times. and has formed philosophical thought for millennia. We just all agree that the altitude and azimuth system with its grids that we saw in the previous video, as well as the ecliptic and equatorial systems, are being portrayed on a sphere. This is just a really helpful map for getting us around the sky. So the two stars, as we can see from this angle, as viewed from Earth, have some angular separation on this sphere. And what does that kind of look like? The celestial sphere, again, is an imaginary sphere around the Earth on which all heavenly objects appear to be located. It appears to rotate around us. We know the Earth is rotating, but we can think of the celestial sphere as rotating around us. The celestial sphere has in the celestial equator. The North Star, Polaris, is near what's called the North Celestial Pole, where nothing appears to rotate around it. And this equator is 90 degrees away from the North Celestial Pole, as well as the South Celestial Pole. Equatorial coordinates are a different way of finding our way around the sky. We can establish that the North Celestial Pole, where Polaris is at 90 degrees north declination, or positive declination. Negative 90 degrees declination is the South Celestial Pole, and this is measured with respect to the celestial equator. The celestial equator is then matched as a kind of is like an extension of latitude out into space. And so that's our good way of thinking about it. And then we can also look at the right ascension, which is the number of hours of angle from the vernal equinox, and the vernal equinox is where the ecliptic meets the celestial equator. The celestial equator is fixed with respect to the stars, and it's the extension of the Earth's equator out into space. The ecliptic is the path that the sun takes, and the vernal equinox is one of two nodes where these two circles intersect. And what we do is we say that we're calling right ascension in hours, not degrees. And so there are 24 hours around the North Celestial Pole, and each of these hours is 15 degrees. That's our way of defining these two coordinates. And that's helpful because when you think about it, you say, oh, wait a second, something that's on the celestial equator, if we wait 1 hour, it will move 15 degrees from its present position. So that's where that really comes from. Right ascension is measured eastward around the celestial sphere. Once again, declination is an angle north or south of the celestial equator towards the poles, and all objects in the sky can be given on terms of these two coordinates. And this is a map on the celestial sphere, which is fixed with respect to the stars. Again, angular measurements are not distance measurements. They are projections on the sky, and we can say on the sky because we're pretending that the sky is this celestial sphere, and things can be greatly distant from each other. Stars can be tens of light years away or thousands of light years away. We just remember that this is a fictitious concept. So what does this mean? It helps to actually look at star trails. Star trails help us understand what we mean by the celestial sphere, and all you have to do is take a camera and open the shutter for some period of time and let the stars move. You have to be in an extremely dark location for this to occur. This is not taken in daylight. This is taken at night, and the reflection off of these rocks is from starlight or even moonlight. What we're looking at here is this particular image taken by Matthew Seville. The stars in this time exposure in the northern sky move counterclockwise around one point. So they seem to be rising on the right in the east and setting in the west on the left. There's almost no motion in the center, and that indicates where the celestial pole is. The altitude off the horizon of the celestial pole indicates your latitude. So if it was directly overhead, you'd be at the North Pole. If it's directly on the horizon, you'd be at the equator. And if it's like 30 or so degrees, it's about 30 or so degrees north latitude. And you can actually tell how long this exposure was by how long the star trail is. And the length of the star trails in this image look less than 1/12 the way around of a circle. So I'm going to guess that this is roughly about a 15-minute exposure. And north is, of course, at the center of this image. East is to the right. Again, Polaris is right in the center, and you can see that's the brighterish star that seems to not be moving. And the only reason that it's much brighter there is simply because it hasn't moved. And because it hasn't moved, it overexposes on the image that you see on the sky. Notice how some stars never rise or set. Those are called circumpolar, and they go below the North celestial pole, below Polaris, and they never go below the horizon. There are a number of stars that are circumpolar. Now, let's look east. This is a different photograph taken by Juan Carlos Casado, and this was published on the theworldatnight.org, and so you can go check that out. But I'm really looking at this concept we're looking at the celestial equator. To the left of this image is to the direction of the North celestial pole, and to the right of this image is towards the South celestial pole. And directly in the middle of this is the celestial equator. This looks like this because we've projected a dome onto a two-dimensional surface and allowed star trails to happen. These star trails, of course, this was a many-hour image, and he also superimposed it he did a secondary exposure on top, and the thing that goes ... across the middle, that's the sun, and this was done at roughly at the equinox, so that the sun could rise due east. But you can see that the star trails appear to curve around the North celestial pole and appear to curve around the South celestial pole, but they seem straight towards the east. And that's what we mean by the celestial. We can think of it as a projection of the latitude out into space. So the latitude of the equator projected out into space is that kind of dashed line, which is representative of the sun. Next time we're going to look at the celestial sphere in greater detail and go over all of these using a sky simulator, Stellarium as well as Sky Safari. We'll see you next time. Now we'll examine the celestial sphere using a simulator. This is Sky Safari, which is a good simulator, but it's not free. We can use it to view the whole sky, and we can orbit the Earth, as well as a lot of other places too. First, let's note the latitude and longitude lines on Earth, with the red longitude line you see there being the prime meridian. The prime meridian is the 0 point for longitude, and the equator is of course the 0 point for latitude. We don't have a lot of these lines on the Earth as they're seen here since they're spaced far apart, but that's okay for our purposes. Most important is the idea that latitude and longitude are fixed with respect to the Earth's surface and act as a coordinate system to help us locate things. If you look at the background grid that seems to be in front of the stars, that is an apparent reflection of the Earth's longitude and latitude out into space. That's the basic idea behind the equatorial coordinate system and its coordinates of right ascension and declination that is imposed upon the celestial sphere. It's a fixed coordinate system with respect to the stars, just in the same way that longitude and latitude are fixed coordinate systems with respect to the Earth. We can see the coordinates around the edge of the screen. The easiest to understand is declination. It's merely a reflection of latitude out into space. We see that there is a celestial equator, which is the projection of the Earth's equator into space and serves as the 0 point for declination. Objects can range from 0 declination up to plus 90 declination in the northern sky and minus 90 degrees declination in the southern sky. Right ascension, on the other hand, is the astronomical equivalent of longitude. Right ascension is the angular distance of an object measured eastward from the first point of Aries, also called the vernal equinox. Unlike longitude, right ascension is usually measured in hours, minutes, and seconds, with 24 hours being a full circle. This means that each hour is about is exactly 15 degrees. Because right ascensions are measured in hours of the rotation of the Earth, they can be used to time the positions of objects in the sky. For example, if a star with a right ascension of 1 hour and 30 minutes and 0 seconds is at the meridian, then a star with right ascension of 20 hours and no minutes and no seconds will be at the same meridian, which is the apparent highest point in the sky due south, at 18.5 sidereal hours later. A sidereal hour is about 10 seconds shorter than your standard solar hour. Your everyday solar clock defines the 24 hours as the time for the sun to return to its original place in the sky, such as noon to noon. The sidereal day defines how long it takes for the stars to return to their original places in the sky. That's about 4 minutes shorter than the solar day due to the Earth's revolution around the sun. Let's go back to the prime meridian, which is the red longitude line. Its analogy in the equatorial coordinate system is where the ecliptic meets the celestial equator, which you can see here now. As you can see from the coordinates around the screen, that's 0 hours right ascension. The ecliptic, of course, meets the celestial equator twice, and this point that we're looking at now is the ascending node, meaning it's the point that the sun travels on as it goes on the ecliptic from below the celestial equator to above it. Nicely, as you can see from the simulation, the date I chose, the planet Neptune is conveniently sitting right at that location. And what exactly is the ecliptic? The ecliptic is the path that the sun appears to take around the sky as seen from Earth. But really, it's the path that the Earth is taking around the sun. It's just that we're on the Earth, so we perceive the sun as moving around the sky on the celestial sphere on the ecliptic. Also, all the planets in the sky stay pretty close to the ecliptic. In fact, most are very close to the ecliptic, except the moon. The moon deviates quite a bit. The reason they all stay very close to the ecliptic is because all of the planets orbit the sun in the same plane. It's a little bit of deviation, just a bit, but not by much. But roughly all the planets go in the same plane. Once you get to planets beyond Neptune, such as the dwarf planet regime, of which Pluto's the largest, things can get really kooky and they're very much non-coplanar. Now let's take a look at an example star and look at its coordinates in this system. When I click on it, I see its name is Markab. If I click on it again, Sky Safari presents all kinds of interesting factoids. If we click then on the Data tab, we can see its equatorial coordinates. We see that Markab's right ascension is 23 hours 5 minutes and 59 seconds, so basically 23 hours and 6 minutes. Its declination is plus 15 degrees and 20 arc minutes. That lines up nicely with what we see in the grid. By eyeball in the grid, it's about halfway between 22 and 0 hours, and it's also just above the celestial equator. Now let's look around the sky to find the location where all the right ascension lines converge. That point is called the North Celestial Pole. We've talked about this in a previous video, but it's worth noting that in that video, we were looking at the horizontal coordinate system of altitude and azimuth, and we used the North Celestial Pole to show us our latitude. That's still of course true, but we'll now use the nearly fixed point of Polaris in the sky to give us a hand. The convergent point of all the right ascension lines is called the North Celestial Pole and is labeled NCP. I want to point out here that the Earth is rotating on its axis, and in our daily lives we don't feel that spin. Let's take a quick moment to ask why that is. We don't feel it because the rotation speed is almost exactly constant. If there were any change at all, you would most certainly feel it. If the Earth magically disappeared and its gravity was no longer present in an instant, you would not be flung outwards. You would fly in the exact direction that your motion of your little patch of the surface of the Earth was pointed at the moment of disappearance. Think of a shot putter or discus thrower or hammer thrower from track and field. The thrown object leaves exactly in the direction it was moving at the moment of release. Here, what's keeping the discus going in a circle is the arm of the athlete. For the Earth, it's the gravity of all the Earth that holds everything in a circle. To learn more about this, see my video on Newton's laws of motion. The important result here is that we're in a rotating reference frame and the sky is fixed, so we see the sky moving from our perspective. Therefore, the equatorial coordinate system is the most natural sky coordinate system for Earth-bound observers. It has 2 0 points that are tied to the Earth, the North Celestial Pole and the equator. As a final thing with Sky Safari before going on, let's recall my previous video on constellations. If you haven't seen that yet, take a moment to go watch that and then come back. I'll now bring them up in this simulation. Let's show the constellations and their names. We can see how they're divided up into these regions around the celestial sphere. They're divided up into regions of right ascension and declination by the light blue lines. Here I have the official boundaries along with the names and the familiar asterisms for each constellation. Notice how the blue lines are configured. They either always go around the north celestial pole, running along declination lines. This is easy to see with the constellations close to the NCP. And the other lines go parallel to the right ascension lines. That's funny to think about spherical trigonometry in this case, because all the angles of intersection are 90 degrees. There are no constellation boundaries that cut diagonally across right ascension and declination. In this way, the entire sky is mapped out into 88 regions, and none of them are the same shape or size. Now let's look at Stellarium, which is another sky simulation software. Let's see what we saw in Sky Safari, but from an Earthbound perspective. First, there's the grid for the equatorial coordinate system with the 0 point of the North Celestial Pole by Alpha Ursa Minoris, which is Polaris, the pole star. Just to confirm that, let's click on it and see there's the information. There it is. That's nice. Polaris, that's its name. Now let's bring up the familiar constellation lines, which are the familiar asterisms. Next, their names, and finally the boundaries. Here, the boundaries are in red, which is flipped from what we saw in Sky Safari. Again, the boundaries run parallel to either declination lines or the right ascension lines. The boundaries for the 88 constellations completely cover the sky. So this is a bit visually busy, and I'm going to turn it all off for the next stuff. Let's explore what the celestial sphere looks like from various locations on Earth, and we'll orient ourselves in different directions. We start at New York City, which is approximately 40 degrees north latitude. Since the pole star is in the sky, we are facing north. You can see things seem to be rotating around the sky. That's because I've set up the time to run rather quickly and to keep the stars in the sky and not deal with the sunrise or sunset, so I've turned off the sun. The grid appears to be rotating. This makes sense because the Earth is rotating and we are on the Earth. From our perspective, where we're observing from a rotating reference frame, of course, things that are not in our frame that are fixed will appear to move. If we look east, we see that the ascending part of the celestial equator is always rising from due east. Higher declination values are to the north, and negative declination values are to the south. Looking south, we see that the stars appear to be circling a point in the sky that is below the horizon. That is, of course, the south celestial pole. We also note that the stars move from east to west along the sky. Finally, looking west, we see the celestial equator intersecting due west at an angle. That angle is also helpful in determining your latitude. The setting angle ranges from 90 degrees at the equator to 0 degrees at the poles. The setting or rising angle is 90 degrees minus your latitude. The altitude of Polaris is more direct, but if you can't see the North Star, then you can watch bright stars near the horizon to get your latitude as well. As we'll see, this works from all other locations on the Earth. Let's bring up the location window to see what the celestial sphere looks like from other locations. Let's change the latitude to the North Pole. At the North Pole, the celestial equator is on the horizon. Therefore, everything appears to circle the horizon. Right now, it's at this time that I'm recording this, which is approximately January of 2024, the sun is below the horizon. The sun never rises at the North Pole in winter. You'll also notice the cardinal directions have disappeared. At the North Pole, all directions are south. East, west, south, north, they're not really defined at all at the North Pole. But if we go 1 degree down from the north, then we do get a north and we do get an east and a south. The stars won't rise much, no more than 1 degree, so it's kind of the same as being right at the North Pole. Let's now go down to the equator, which is 0 degrees latitude. We're looking east. The celestial equator comes straight up from the horizon at a 90-degree angle. 0 latitude means a 90-degree rise angle. Let's now look south. The south celestial pole is on the horizon. Looking west, everything's set straight down to the horizon, just like looking east. Looking north, we see the north celestial pole on the horizon. So now let's go to a southern location. Say 40 degrees south latitude. Now the north celestial pole Polaris, is below the horizon. Stars still rise in the east and set in the west, but because of our location, stars move differently than those in the northern hemisphere. To show this, let's look due east. Stars are still rising in the east, but they're rising at an angle that makes them go up and to the left as opposed to up and to the right. That's because the south celestial pole is in the sky. Looking there, there's no obvious star right next to the south celestial pole. Bringing back the constellation lines and names for a moment, we can see that the Southern Cross is in the sky. The constellation named Crux is also called the Southern Cross. It has two stars that, if you make a line between them, point to the south celestial pole. The Southern Cross provides a helpful way of finding your way around the sky in the southern hemisphere. So now let's explore the South Pole and see what that looks like. So we enter south 90 degrees. At the South Pole, the celestial equator is again along the horizon, and again the south celestial pole is at the zenith, just like the situation at the North Pole. Moving 1 degree off the South Pole, we get our north, south, and east and west again. So now let's return home. The celestial sphere is a coordinate system that is fixed with respect to the stars. Its reference points are due to special points on the rotating Earth. The North Celestial Pole and South Celestial Pole are directly overhead the Earth's poles, and the celestial equator is the extension of the Earth's equator out into space. Hi, just as looking at the nature of what the sunrise and sunsets are like and the sun's motion across the sky. We know that the sun rises in the east and sets in the west, just like the stars. But over time, the sun drifts slowly eastward relative to those stars. And what we're watching here is the diurnal motion of the sun rising in the east and setting in the west to very speed up over the course of the day. However, the eastward drift relative to the stars takes about 365.25 days to return to the same location in the sky. That's 1 year. And therefore, a leap day occurs every year, every 4 years, because that extra 0.25 days accumulates into 1 day. And so we calendarize that by adding a leap year once every 4 years. But the sun itself just slowly drifts over time. And so we have to see why it does that with respect to the background stars. So let's take a look. The Earth has an orbital motion that makes it look a little different. The rate at which the Earth goes around the sun is different than the rate at which the Earth turns on its axis. That creates a difference in the position of where the sun appears to be in the sky. The solar day is what we call noon to noon. That's what we call the day. Everybody says what time of day it is, and they say it's noon or 1 p.m. That's time according to the sun, and that is the expected diurnal motion. Well, the sidereal day, though, is the day according to the positions of the distant stars. We call the normal day, or the solar day, this way, but if we look at the sidereal day, it is shorter by about 4 minutes. That means that the Earth has to turn just a little bit more to get the sun back in position for noon to noon, right? Otherwise, if we were telling this time by the stars, we could do that. We could have said the day is defined by when, say, Orion is directly overhead, or this star is directly overhead at midnight or something, when it is due south or due east. If there was some particularly bright star that we could see all the time, maybe like Betelgeuse goes supernova or something, and we could see it in the daytime, it's possible that we could tell the time by Betelgeuse then, because if it lasted for centuries and centuries, and most of human civilization, or we had another distant star that we saw. But anyway, we tell the time of day by the sun. But the sidereal day is different. We have 3 diagrams, A, B, and C, and we have a position on the Earth, capital A, and capital A looks at the sun in the first image when the sun is at noon. So then what happens is, as the Earth goes around its orbit a little bit, right? So we change from that bottom dashed line to the dashed line that's moved up a little bit. And if we go all the way around but have A pointed in the same direction, meaning looking at the same stars in the sky, stars are much more distant than the sun, so therefore they appear to be fixed on the sky, as opposed to the sun, which appears to move with respect to these background stars. So the stars themselves appear to come back to the same point in the sky in 23 hours and about 56 minutes. Now then, you got to move around a little bit further on the circle, just about a degree, which is 0.986 degrees, which is about 4 minutes of time to get to noon on the solar day in the bottom one. So those are the differences between those two things. And as a result of this Earth's motion around the sun and the difference between the sidereal and the solar day, the sun appears to move around the sky. And it does so on a path. And that path is called the ecliptic. And that is the path the sun apparently takes in the sky because of the difference in time between the solar day and the sidereal day. That happens because the Earth is going around the sun. The sun traces a path that looks like that curve. The red dash thing is the celestial equator, which is the projection of the Earth's rotation, the Earth's equator out into space. And the reason that the ecliptic, which is the path the sun takes that around the sky, is different than the celestial equator is because the Earth's rotation axis is tilted with respect to its orbital axis. But more on that later. The zodiac are the constellations through which the sun passes on its path around the ecliptic. So we have the celestial equator, which is the projection out into space of the Earth's equator. We have the ecliptic, which is the path that the sun takes in the sky. And the zodiac are the constellations through which it passes. So let's look at those particular zodiacal constellations. In October, you see it's in Virgo. November, it's in Libra. December, it's in Scorpius. Most of December, though, it's in Ophiuchus, different one. Sagittarius in January, Capricornus in February, Aquarius in March, Pisces in April, Aries in May, Taurus in June, Gemini in July, Cancer roughly in August, and Leo roughly in September. These are rough things, but you'll notice they all sound very familiar. Those are the astrological zodiacal constellations, and you're very familiar with them from people spouting about them, but this is what this means. That's all that it means. So let's take a closer look. We can look at the zodiacal constellations, and now we're taking a much tighter look. Now we're isolating the sun in this video at noon throughout a number of years. And we see the progression of the sun as we're going really fast. We're doing many days per month. And there we go. We see, I put the artwork up. I put the boundaries of the constellations up and the lines that commonly show asterisms as well as the names. Now, of course, we don't see these artwork in the sky, the red boundaries in the sky, nor do we see the names or any of the lines connecting them. But the ecliptic is the path that the sun is going on, given at a given time of year, given date, shows where it is in the sky. It's kind of weird that that line seems to be moving, but it's not. It's the sun that's moving along the line, and we're looking at noon, or 1 p.m., or noon, depending on what the daylight savings hour is, where the sun is we're looking due south every solar day. So we're isolating it solar day by solar day. If we were isolating it by sidereal day, then the stars would stay fixed and then the sun would appear to move. As you can think about it, just imagine that we're fixing the stars in the background, and the sun would then definitely seem to move with respect to those background stars and background constellations. Notice over that we've looked at a number of years. It's now on the simulation up to 2030, and we're maintaining the same constellations. Now, the Earth's precession on its axis will change things, will change the position of the ecliptic, or more specifically, it'll change where the ecliptic meets the celestial equator. When we get to that point, that is the autumnal equinox. When we get to that point, that's the winter solstice. This is the vernal equinox or spring equinox. And up here is the summer solstice. And that's when the sun is highest in the sky at noon. That's when the sun is up for only 12 hours. And this is when the sun is up for the shortest amount of time during the year. And there it is. And that was used, video was used using stellarium. So let's go back again and look at it. And instead of moving through the sky, we can see as the Earth moves around the sun, we look in the direction of the sun, and it appears to be in these constellations. And the tilt of the Earth's axis of rotation with respect to that orbital plane means that the band, the blue band that goes all the way around, is not the same as the orbital axis, which is the dashed line. That thing is tilted. So this kind of diagram is a little bit goofy. And still we can then look at it from the other perspective to say, well, what's in the night sky at midnight during these times? It's like, oh, okay, so in September, Pisces is up at midnight. In December, Gemini's up at midnight, or at least 100%, 180 degrees away from the sun in the sky. In March, Virgo is 100%, 180 degrees. Why am I saying 100%? 180 degrees away from the sky from the sun. And in June, Sagittarius is up. And this gives us rise to what we see as the summer constellations and the winter constellations. Gemini is a winter constellation. Sagittarius is a summer constellation. Pisces is a fall constellation. Virgo is a spring constellation. And this shows the zodiacal positions of the constellations at midnight. Again, we're not taking into account the difference between the Earth's orbit and Earth's orbit and its axial tilt. We're not taking into account with this particular thing, but we do in this diagram. See, now we're seeing in this diagram where the positions of the winter and summer solstices are, where the autumnal and vernal equinoxes are. The vernal equinox occurs when the sun is traveling on the ecliptic and it crosses from south of the celestial equator to north of the celestial equator. It's also where we define the right ascension and declination of the equatorial coordinate system. If we look at it from a purely geocentric standpoint, which we shouldn't, I guess it's very helpful in this regard, because now we can look at what we apparently see, and we see that in the sky, straight up from the Earth's axis of rotation is the north celestial pole, the celestial equator is the extension of the Earth's equator out into space, and the sun appears to make a path in the sky that is tilted 23.5 degrees. But really, that tilt is actually the Earth's orbit around the sun, and the axis is tilted with respect to 23.5 degrees. So this is the geocentric view of things, but really we should have a heliocentric view, which we've shown, but this helps us understand what the ecliptic is and why it seems to go up and down based on how we appear to see it. Once again, geocentrism is dead wrong. Let's look again for the reason for the seasons. Frequently, when we look at the seasons, we say, oh, it's warmer in the summer and cooler in the winter. For the northern hemisphere, it's warmer in the summer. For everybody, it's whatever summer it is, it's warmer in your summer and cooler in winter. Why is that? So what is the reason for the seasons? Reason for the season is the tilt of the Earth's axis with respect to its orbital plane. The altitude of an object off the horizon is the height of that celestial object measured at an angle above the horizon. And the sun has a higher altitude in the summer than it does in the winter in the northern hemisphere. And the solstice are the points on the celestial sphere where the sun reaches its northernmost and southernmost points. And in the northernmost points, that's around June 21. And the southernmost points in the winter solstice, that's about December 21. The equinoxes are places in the celestial sphere where the sun crosses the celestial equator. That's about March 21st for the spring. And the autumnal equinox is about September 22nd. When we look at the sun on the solstices, well, actually, on the summer solstice specifically, the sun appears to be very high in the sky. It casts very short shadows. The Earth is warm. The sun is warm. And it rises very far north of east, and it sets north of west. And when it's at noon, it is high in the sky. That's belied by those kind of simulations I show, which will look at the sun. But if you think about it, the sun in the previous simulations looked high in the sky at noon when it was in the summertime. Well, we didn't take into account the fact that the sun rose and set. We were just jumping forward 24 hours at a time in that simulation. But if we watch the sun, we would see it would rise very far north of east, get to that high point, and set very far north of west. And so notice that the length of the shadows is short, and the days then, therefore, because the sun is in the sky longer, would be longer. That's important to know. But the short shadows are a key. Next, we can look at the winter solstice. Obviously, since the sun rises south of east and sets south of west, and it gets lower in the sky, the shadows are in general longer, and the sun is up for shorter periods of time. It's a very familiar thing, the winter days as they approach, the days get shorter, and the sun rises later and it sets earlier. And that's what we see. That's what we see here. In the winter solstice, the sun is not up above the horizon as much. And at the equinoxes, the sun rises due east and sets due west. And that's the effect of this tilt of the Earth's axis and the Earth going around the sun. All right, so why do we care about shadows? This is why. Because the angle of incidence of the source of light on the Earth distributes the light differently. If something is beaming straight down on a surface, the light doesn't spread out that much. And in fact, the spot is smaller. But if there's a larger angle, then the beam of light, all the light gets spread out onto a larger surface area. So when you have the sun straight up, the beams of light do not spread out over larger surface areas, and therefore you have more intense heating per square inch on the surface of the Earth. That's what the left-hand side flashlight idea is representing. But in the winter solstice, when the sun is low to the horizon at noon, the sun's light is spread out over a larger surface area per square inch, and therefore it is less intense per square inch, and therefore there's less, the intensity of light is less, which means the energy that is received by the ground is less per square inch. That means there's not more energy, and it doesn't get as hot. That's the reason for the seasons. It is the angle of incidence of the light on the Earth distributing the light less and less intensely at winter than it does in the summer. Let's look at that effect on the next slide. Here we see it quite explicitly when we look at the left-hand side. The effect of that flashlighty thing on the left is that the smaller ground area is covered by the light from the sun for the same amount of rays of beams. Let's say you have 3 beams, they would hit a smaller surface area, which means they would be more intense and deliver all their light into a smaller surface area, which means that surface area would get more energy per square inch on the surface. In the wintertime, or late in the afternoon, or even late in the day when the sun is setting, it's actually less intense. Why? Because the light from the sun is being spread out per square inch over a larger surface area, and that's what we see on the right. So in the wintertime, it's all day like this. And it's always like this at sunrise and sunset for every day of the year. But at noon, let's just look strictly speaking at noon. At noon in the winter, it's like the right-hand side, and at noon in the summer, it's like on the left-hand side. The intensity of the light is what creates the heat per square inch on the surface of the Earth. And that's where the seasons come from. It is not due to the distance between the Earth and the sun. In fact, we are closer in the northern hemisphere to the sun during the winter than we are at summer. And that's just the position of it's the nature of the ellipticity of the Earth's orbit, which is very small, very small. So if it were about the distance, then we would be hotter in the winter, or it's not. The angle of incidence of the sun's light on the surface of the Earth drives everything. That's what we have as the reason for the seasons. They're caused by the relative tilt of the Earth's axis with respect to its orbital plane, and it's not due to the distance from the sun. All right, so we talked a little bit about the zodiac. We talked a little bit about rising and setting of the sun. We talked about the sun's motion throughout the day, the sidereal day, the solar day, all of these things. We'll talk to you next time. Did you ever notice that we only ever see one side of the moon? The moon's period of rotation equals its period of revolution around the Earth. That's a really interesting fact. The rotation of an object is something that spins about on an axis that points down through it. And the revolution is the orbiting of one object around another. Here, the moon around the Earth. It's really interesting that the moon rotates with the same speed at which it revolves. Funny enough, if it did not rotate, a feature on its surface, such as these craters you see in this image, would always point in the same direction in space. And then we would see it move into and out of view. That into and out of view would make it look like, from the ground, that it's rotating, when in fact it would not be. But because this is so weird, we look up at the moon in the sky and we think that it's not rotating. So let's actually go through and look at all the phases of the moon, the nature of the month, all these things, and show why it is rotating. Let's go through all the phases. First we start with waxing crescent, and then we get to approximately almost a week in, we get to the first quarter moon, which is half illuminated, and then we go to the waxing gibbous moons, which are not fully illuminated. Finally we get to full moon, and then it's waning gibbous, which is more than half illuminated. Then we finally get to third quarter, which is roughly half, and then less than half illuminated are the crescents, the waning crescents. And I leave the black spot portion open simply because that's called the new moon. New moon is when the moon is in the same direction in the sky as the sun. So let's see how we get those phases. But first, let's take that really quick trip into why the moon rotates at the same rate as it revolves. Okay. The moon shows its phases because sometimes it's on the sunward side of the Earth and sometimes it's not. So what we have here is a cartoon of the moon and the Earth, and I've put a red line through the moon just to demark the side that we see from Earth. Yeah, this is kind of a goofy thing because the North Pole is not through the center, through the equator, so I probably should have used a different little cartoon there for the Earth, and I guess I could. But the most important thing is we're pretending that we're looking straight down on the North Pole of the Earth or the North Pole of the Moon. We're also pretending that these axes of rotation and revolution are all the same, which is not true. But anyway, most important thing is that red line. So let's now see what happens when we let it go. As we see, the moon is going around the Earth, and that red line is staying fixed with respect to the moon. But yet, if you look closely at the red line, that would seem to indicate that it's rotating. Because if the red line weren't rotating, it wouldn't change orientation. In fact, it changed 360-degree rotation. You can do that for yourself by just kind of thinking about it, taking a pencil and put it in your hand, and then rotating it. The stick will rotate around. Now, if your hand is holding the stick, and it goes around, you can actually rotate the stick by moving your wrist around in a circle and keeping the pencil in orientation the same way as your hand. Another way to look at it is this. As the moon goes around the Earth, we can either have option A or option B. Option A is the moon is not rotating as it revolves. So if the moon did not rotate at all as it revolved, then that black spot, which is some feature like a crater, would always be pointed in the same direction. To us on Earth, it would look like the black spot is moving across the moon. But in reality, the moon is not rotating on its axis. It is certainly revolving around the Earth, but it certainly is not rotating on its axis. However, in B, to the right, we see that the orbit is still the same, where it's orbiting around Earth, but now we're allowing the moon to rotate on its axis at the exact same rate as which it revolves. That black spot is staying fixed with respect to the position, it's always facing the Earth. Now, that's interesting. This is a result of tidal locking for the Earth and Moon system. The Moon used to be, during its formation about 4 billion years ago, when it was formed, it was much, much, much closer to the Earth than it was today. It also was going around the Earth a lot faster, and it was spinning a lot faster. those two things decreased. First, the distance went out. First, the moon went to a greater distance over time, and the rotation slowed until it matched the month. That's called tidal locking. I talk about that in another video. So let's actually now look at what we mean by a month. First, we're going to review what we talked about last time, which was the sidereal versus the solar day. That's kind of helpful. The sidereal day is when the sun comes back to the same position in the sky with respect to the distant stars, but the solar day is when the sun comes back to, say, due south at noon. That's the difference between them. It's the same position in the sky with the same place with respect to the ground at the Earth, but the sun will change its position with respect to the distant stars. And that's because the Earth is going around the sun. Similarly, we can derive sidereal and synodic periods for the moon going around the Earth. The first one, which we'll call the sidereal month, which is approximately 317 days. The sidereal period is the time it takes for one revolution of the moon around the Earth with respect to the distant stars. So that's going from spot A below, and as the Earth goes around the sun, it gets to spot B. In that time frame, the moon has gone around the Earth and gotten back to that place. That, if you're looking down from above the solar system, the sidereal month is probably the most intuitive definition of what a lunar orbit would be. But we're based on the Earth. So we use the synodic month. That's 29.53 days. The synodic month is the time interval between successive similar alignments of the moon and sun. From the standpoint of an Earth observer, the synodic month is probably our most intuitive definition. When we look at the moon, the easiest thing is to recognize the phase rather than precisely where it is among the stars, its position. So that's how we do things. As such, the synodic month is the time between, say, full moons or between, say, new moons. Both of these are called syzygies, which are either conjunctions or oppositions. But it's when the sun, the Earth, and the moon are in a line. That's a syzygy. The difference from a sidereal month compared to a synodic month is because the Earth goes around the sun. So now we have these two different kinds of months. The synodic month, which is what we call phase to phase, or full moon to full moon, or new moon to new moon, or even crescent to crescent, or specific first quarter to first quarter, whatever you like to call it. That is 29.5 days. That is the synodic month. The sidereal month is much shorter, by 2.2 days, which means there's approximately an additional sidereal month per year compared to the synodic month. All right, let's see how that plays out together. And let's look at the moon's phases. And we're going to look at the synodic month phases at this point. So let's start here. On the left-hand side, we see the rays of the light from the sun. On the right-hand side, I'm going to show the various phases of the moon and their names. This is named a waxing crescent moon. I still use that funny little graphic, which, we're not really looking straight down on the Earth for this one, but hey, we're, what's a diagram among friends? It's the Earth. So the orbit is represented there, and now we have two different dashed lines. I've replaced the red dashed line previously and made it blue to indicate the far side of the moon and the near side. The far side we'll never see. It never is up in the sky for us to see from Earth. The near side is. But we now need a new demarcation. The side that's illuminated by the sun and the side that's not illuminated by the sun. As we can see, I've shaded out the side on the right-hand side because that's the side that's not illuminated by the sun. But there's part of it that we can see, and part of it, well, all of the side that we can see, more than half of it is not illuminated. As you can see, the grayish spot is a big chunk of it that is taken out, that is on our side, on the Earth side of the blue line, is more than half of it is grayed out. And a very small wedge is not. That corresponds to a waxing crescent. So that little disk on the lower left is represented on the right by a spherical distribution. The moon is a sphere, not a disk. So a little pizza pie wedge, like we see in the lower left, becomes that crescent wedge. So if you were to take the crescent wedge of the moon and look at it from above, it would look like that pizza slice. Well, it would be projected down. But we look at it from the surface of the Earth and we see the poles at either end. So the tips of the crescent, the horns of the crescent, are at the poles, the north and south pole of the moon. So now let's go forward. First, though, we call this a waxing crescent moon. Waxing crescent moons are somewhere between 90 degrees and 0 degrees elongation east of the sun. They set just after the sun sets. So if you see a waxing crescent moon, the sun will set and then the moon will set. Roughly speaking, this image of the waxing crescent moon is a 4-day-old moon, and the moon is in the sky, in the daytime sky, mostly during the day. Daytime sky, of course it's daytime sky during the day, but the moon is, of course, when it's in this phase, mostly up during the day. Now we move along to the first quarter moon. The first quarter moon, this is about 7 days since new moon, and it is 90 degrees elongation east from the sun. It is half illuminated. And why is it called first quarter? Well, it's 1/4 the way around, and 1/4 of the moon is what we can see to be illuminated. That's why we would call it first quarter. There's multiple reasons, but 1/4 the way around from new. So this moon then will set at approximately midnight, and it will rise at approximately noon. So let's see what we have next. And the moon goes around the Earth, and now we get to these waxing gibbous moons. The waxing gibbous moon will rise sometime in the late afternoon and will be up most of the night and then will set sometime a little bit after midnight. This is roughly a 10-day-old moon, and it has an elongation angle from the sun between 90 and 180 degrees. Next, we have the full moon. Full moon is 180 degrees away from the sun in the sky. It's about 14 days in, and yes, it's directly opposite the moon, the sun from in the sky, so it rises at sunset and sets at sunrise. Next, we go to the waning gibbous moon, and this is roughly 18-day-old moon. It's at 90 and 180 degrees west of the sun. This will rise sometime after sunset. It will be up most of the night and set after sunrise. Then we go to third quarter moon, which rises at midnight, and it's about a 22-day-old moon. It's 90 degrees west of the sun in the sky. It rises at midnight and sets at noon. Next, we go to the waning crescent moons, which rise just before sunrise. This is a 26-day-old moon, and the elongation angle between it and the sun is somewhere between 0 and 90 degrees west of the sun. So it rises just before sunrise and then stays up most of the day. Finally, we have new moon. New moon means we don't see it in the sky because it's in the same direction as the sun in the sky, and it's up all day. It rises at sunrise and sets at sunset. New moons are important because that's when solar eclipses happen. If it's new moon, then they can have a solar eclipse. That's what we call a 0-day-old moon or new moon. All right, so we're back to waxing crescent again, and the cycle repeats and repeats and repeats over time, and we've seen these happen throughout most of our lives. But now, sometimes there are people that say, well, hey, I see all this, but the moon's pretty big, and the Earth is really big. So a lot of people have this mistaken idea that the dark part of the moon that we see is due to the Earth's shadow. It is most certainly not due to the Earth's shadow. So let's see really why not. Well, first let's start off with the idea that the Earth is about 8,000 miles wide. That's about 12,730 kilometers or so. And now we're going to zoom out, and we're going to show how far away the moon is from the Earth. The moon is almost 240,000 miles away, which is 385,000 kilometers. The moon itself is only 2,100 or 2,150 miles across, or about 3,500 kilometers across. And there's only one time that the moon will be in the shadow of the Earth. And let's say if the sun is off to the left in this diagram, and then the moon would have to be off to the right, because look at that. That's a very tiny target. So now we're going to add the orbital path, and after we add the orbital path of the moon around the Earth, now we're going to zoom out and take a look. Look at that. Look at how many places that it's not in the shadow. The sunlight's coming from the left, and the Earth is a very, very, very tiny target. And I've tried to make these things as exact as I could in terms of their proportionate sizes. This is pretty close to it. So therefore, the moon is only going to be in Earth's shadow for a very small period of time, but it's not necessarily going to always be in the Earth's shadow when it gets on the far side of the Earth compared to the sun. This is a really important point, and this is why. It is completely why that the phases are not due to the shadow of the Earth on the moon. They are due to the positioning, the relative position of the Earth, moon, and sun in the sky. Okay, when you hear about stuff, occasionally you hear about in the news this thing called like a supermoon. What the heck is a supermoon? Well, the moon travels around around the Earth in an elliptical orbit, or it's not actually a circle. I was kind of deceptive in my previous stuff. It's not a circle. It travels in an ellipse. The moon therefore passes through a point closest to the Earth called the perigee, and a point farthest from the Earth, the apogee. And when the moon is at or near its closest point to the Earth at the same time as it's full, we call it a supermoon. Why? Because that's a great way to get people to come outside and go look at the moon and have a good time. It's also great for stuff, to relate to the news people. And you'll see stuff about the news. Oh, go outside and see today's supermoon. You won't miss it tomorrow. And people go, I missed the supermoon. Doesn't have a cape on it, not flying around. It's not 60 times the size. No, it's just a little bit closer than it normally is. And what's the difference between them? See, it's kind of a funny thing. But it will appear larger in the sky. But how much larger? Well, noticeably, but not necessarily to most people's eyes, but you could notice it if you know what to look for. So it can actually be up to 14% bigger because the moon's orbit wobbles and it differs depending on where the sun and Earth are in their orbits, and the exact distance on these closest and furthest points do vary. Here are the various differences that we can have between a supermoon on the left and a micromoon on the right. A micromoon is usually nothing that makes news. A micromoon is when it's full and it's at apogee, when it's at its farthest point to the sky. So that's, the only difference between the micromoon and the supermoon is about 14%. And each of these is between, say, 34 arc minutes on the left and 30 arc minutes on the right. And 30 arc minutes is half a degree. 34 arc minutes is a little bit more than half a degree. So it's a little tricky to actually see these in the sky, but your eye can actually make the sound go, wow, it does look bigger. And it's not just because it's low to the horizon either. Having the moon low to the horizon is a psychological trick, not necessarily a reality trick. That's kind of fun. But supermoon, micromoon, what other some moon names? Well, there's blue moon, wolf moon, snow moon, worm moon, pink moon, flower moon, strawberry moon, buck moon, sturgeon moon, harvest moon, full corn moon, hunter's moon, beaver moon, and cold moon. All of these things are very traditional. They come from the Farmer's Almanac. The blue moon is just simply 2 full moons in 1 calendar month. And it's not that rare. It happens at least once a year. Blue moon, once in a blue moon. Okay, once a year is basically what that means. So if somebody says, oh, it only happens once in a blue moon, that's once a year. Good for them. Okay, but there are other kinds of moons as well. Months as well. But we're going to talk about the 3 other kinds now. There's the tropical month, the anomalistic month, and the draconic month. The tropical month is equinox to equinox, and the anomalistic month is perigee to perigee, and draconic month is node to node. Wow, what do those things mean? Okay, they are not described in this image, so I'm going to describe them to you briefly, then I'm going to show you a video. But first, the tropical month is a minor variation of the sidereal month, so it's like the one that goes from A to B. But instead of using the fixed stars, it uses the March equinox. The March equinox is the defining celestial longitude of right ascension in the equatorial coordinate system. It is where the ecliptic and the celestial equator meet on the ascending node. That is the definition of the March equinox. Because the Earth precesses on its axis, The equinoxes also slowly precess retrograde. This means that the moon arrives at this reference frame slightly faster than the truly inertial sidereal frame, and therefore the tropical month is slightly shorter than the sidereal month. By how slight? The period of precession of the equinoxes is about 26,000 years, so it's a very, very, very tiny change from the sidereal month. Next, the anomalistic month, which is an important one as well. The anomalistic month is also a variation of the sidereal month. It's a slightly different flavor, and it's about 27.55 days. Now, what is this then? Is the reference line is instead the line of apsides, meaning the line on the or between the 2 points on the moon's orbit between apogee and perigee, between the highest point in an orbit from the Earth and the lowest point, apogee and perigee. The line of apsides in the moon's orbit precesses about just under 9 years, and so it takes for the moon a little bit longer to reach the same point in the apsidal frame, say apogee to apogee, and it's a little bit longer than the sidereal month. Finally, of these 3 different months is the draconitic month or draconic month. That's 27.2 days. The draconic month is similar to the anomalistic month, except that instead of using the line of apsides, it is using the line of nodes. The line of nodes is the intersection of the plane of the moon's orbit around the Earth and the plane of the Earth's orbit around the sun. Let's get that again. The Earth's orbit around, so the moon has an orbital plane, and it's tilted with respect to the Earth's orbital plane around the sun, which is called the ecliptic. On one end of the line of nodes is an ascending node, and the other end is a descending node, meaning where the moon passes upward through the ecliptic going upward, and the other one where it's passing through the ecliptic going downward. The line of nodes precesses with a period of about just under 18.5 years in the opposite direction of the moon's orbit. Therefore, the draconitic month or draconic month is faster than a sidereal month. Once again, we have the tropical month, which is equinox to equinox. Anomalistic month is perigee to perigee. Draconic month or draconitic month is node to node. And now I got a little video that's going to show that, and we're going to see how these things differ in their appearance. We see first that it's passing by the equinox. That's the March equinox. And now it goes on its merry way, and there's the red line. The red line is the moon. Oh, wait a second. There's a total solar eclipse coming up on April 8th, 2024, when the node matches the when the full moon and the sun is right next to that location. That's how you get that. And that happens only very infrequently. So if we look really closely, let's just look at this again. And I've slowed it down a lot so we can actually watch it. The ascending node of the red line matches that of the ecliptic. And if they just line up perfectly and the distance from the sun is at, say, perigee, not apogee, then the moon will be the same size as the sun or a little bit bigger and totally covered for a total solar eclipse. Now this has been set up to be at New York City, so it doesn't quite cover it. You have to be in exactly the right place in order for the moon to totally cover the sun. And it's called the draconitic month. And see, you can see the node of the intersection right there off to the right. It's called the draconitic month because Draco the dragon is said to live at the nodes, a historical dragon, and it eats the moon. That doesn't eat the moon, it eats the sun during eclipses. And that's pretty cool. Anyway, so that is the ascending node. It's the beginning of the draconitic month. Anyway, so the moon is traveling on its red line, which is the path that the moon takes around the Earth. That is the orbital path around the Earth. And the ecliptic is the orange line, which is the path that the sun takes, which is actually the Earth's path around the sun. So as the moon goes around, we see the phases. We also see a funny thing, because stellarium, which I'm using here to do this simulation, is making it look like that orbit is wobbling. But really what I'm doing, because stellarium is actually measuring the position in the sky of the moon from the Earth's surface, not from not from some location that is representative of, say, the center of the Earth. Oh, and what we just saw there was the descending node, where where the moon's orbit goes through the ecliptic. So that's one, though we've just seen both nodes where the moon's orbit crosses the ecliptic, going down, and initially we saw it going up. There's also an orbital period with respect to the celestial sphere, which is the March equinox, which is where the ecliptic meets the celestial equator. So we're getting closer and closer to that, but we see it's kind of a bother to see the thing moving like that. If we really wanted to see it differently from the moon, we would pretend that the Earth is a dot in space and move from there. And now we're back to the point of Aries, or the equinox, and that's one of the months. And then we go back over here. Now notice we get to this ending point here, and the sun is no longer at the node that's on the lower right. So we have the ascending node of the moon's orbit, and we have the yellow line, which is the ecliptic. Once again, the tropical month is when we got back to that little point that had the Aries thing on it. That was the equinox to equinox. And that's just a point in the sky with respect to the celestial sphere. And that changes because of precession of the Earth's the precession of the Earth's axis. I did not do the anomalistic month of perigee to perigee on this thing because that'd be just harder to see, and we'd have to look at a whole bunch of numbers in the upper left. But anyway, that's a little bit about months and lunar phases and all sorts of wonderful names and things. See you soon. Now we're going to be talking about lunar eclipses. This is a video I took on October 8th of 2014 at about 5 o'clock in the morning from a park in northern Manhattan. This was the beginning of a total lunar eclipse that was visible in New York City. Oh, there goes a plane. Look at that. Eclipses are truly fascinating things. You can see here, the shadow of the Earth is arcing across the moon in a way that you don't see with the phases of the moon. This eventually developed into a full total lunar eclipse, but unfortunately for New York City, on that date, the moon was set before totality. So now let's take a look at what we can see when lunar eclipses occur, where the moon passes into the Earth's shadow. These are 3 exposures of the moon taken before, during, and after a total lunar eclipse, and specifically this is the one on September 27, 1996. And that was kind of an interesting one for me, because I was at a Broadway show that night, Christopher Durang's Sex and Longing, starring Sigourney Weaver. And during intermission, everybody went outside to look up at the lunar eclipse, and it was fascinating to see that over Broadway. So we all stood in the street, we looked up, but then the bell rang for the second act, and my brother really wanted to go back to see the show, so back we all went in. Luckily, the show was really good, but we were able to catch the rest of the lunar eclipse after the show. So let's look at more about lunar eclipses. So if you have a penumbral lunar eclipse, here's the configuration. So the moon has to get into the Earth's shadow. And so this is, of course, really not to scale, really not to scale. I'm showing some lines, the boundary of the lines that demark the umbra, or the darkest parts of the Earth's shadow from the sun. And this is anywhere in the umbra, the Earth is completely blocking out all the light of the sun. The penumbra, that the sun is not completely blocked out by the Earth. When it's in the penumbra, like we saw in the video at the beginning, there was a chunk taken out, and that was still in the penumbra. The chunk that seemed to be fully taken out was in the umbra, so as time progressed, it certainly looked more and more like it was going into the umbra. The penumbra just looks a little dimmer, but the umbra is very extraordinarily dark. So if we go ahead a little bit more in time as the moon goes around in its orbit, if it passes fully into the umbra, then it's called a total lunar eclipse. Sometimes it just has a partial lunar eclipse like we saw at the beginning. That would be considered a partial if the moon just did that, and that happens frequently as well. All right, so let's look at the different kinds of eclipses that the moon can have. And they are the penumbral, which is at the top. And then we have the partial eclipses, which are at the bottom. Those would be partial, just like that. We see a little bit of dimming, but then there's more dimming because it goes in the umbra, just like we saw at the beginning. And then finally, a total lunar eclipse where this moon passes completely into the umbral shadow of the Earth. It's also important to note that these don't happen every month. They don't. And the reason is because the moon's orbit is tilted 5 degrees with respect to the Earth's orbit around the sun. So the moon's orbit does not, so the moon doesn't always pass through the shadow. And therefore, we have to look for eclipses during eclipse seasons. And eclipse seasons are when the line of nodes, which is that red line, lines up. So let's see what we have. Because of this tilt of moon's orbit with respect to the Earth's orbit around the sun, they simply don't happen every month because of that tilt. And the ecliptic is the path that's the big blue area, but the tilt is the tilt of the moon's orbit. So at this time in the moon's orbit, if the moon's orbit around the sun, there will be no way at any time for there to be a lunar eclipse because the line of nodes does not point at the sun. Now, if we go across, say, to 6 months later, again, there won't be any eclipses there because the moon is either below the ecliptic or above it. And now, if we get to this point in when the nodes line up and point at the sun, they can happen here. The red line is called the line of nodes, and this is the intersection where the moon's orbit intersects with the ecliptic. However, it might not happen if the moon is not at the line of nodes for, say, a new moon. So if it's not in new moon phase, then you won't get a total solar eclipse. And if it's not at full moon, you won't get a total or even partial or even penumbral lunar eclipse. So the moon has to be at the line of nodes on that day. And likewise, 6 months later, it might happen there too. But it certainly seems a little weird because it looks like I'm drawing it that they're always at the same time, so you should be able to line this up. However, the line of nodes also precesses, so that means its location changes with time. So really, after about a year, it's more like that. So the line of nodes gets back to its position prior to 365.25 days. And so you can have 3 lineups of the line of nodes during a calendar year. And that's because the Draconitic month, which is the month according to the line of nodes, when it gets, say, from the one ascending node to one descending node, that happens in a 27.2 days compared to, say, the calendar month or the month according to the phases, which is about 29 days. Now, the line of nodes itself precesses with a period of 18.6 years. That whole plane will make one full kind of swing around every 18 years. Therefore, we do know that the line of nodes will point to the sun roughly 3 times a year. That's a bit about lunar eclipses, and I'd like to show you some wonderful pictures that I took. The first one this is a series of photos from Inwood Hill Park in New York City. This was a total lunar eclipse. I took these pictures on October 8th of 2014 at about 5 o'clock in the morning, and you can see the time is progressing and it's getting more and more and more covered as time goes on. And it was about 5:58 in the morning when I had to start packing it in, because it was getting close to sunrise, the moon was setting fast, it was also getting really cloudy, as you saw from the video at the beginning. And this started roughly about 5 o'clock in the morning, and it progresses rapidly over about an hour. I'm just going to give you a different one. This was from September 27 of 2015, and I took this one too. This was near the end of the eclipse. This was about 10 o'clock p.m. on September 27th of 2015. It begs the question, why are total lunar eclipses red? Well, total lunar eclipses, when you go out and see them, they look deep, deep red. It's like, why would they look really red? And so the answer is because we're looking at the refracted light from a ring of sunsets. If you were on the moon looking up at the Earth during a total lunar eclipse, unlike a solar eclipse, because the moon has no atmosphere, during a solar eclipse, you see the atmosphere of the sun, and you can see, which we'll talk about in another video about total solar eclipses. In a total lunar eclipse, if you were looking from the moon back to the Earth, you would see the atmosphere of the Earth glowing red, because the Earth's atmosphere scatters blue light better than red. So the light that gets passed through on this ring around the Earth, that would be the atmosphere that you would see if you were on the moon looking towards the Earth. It would look this bright, bright, bright red, and that would make the moon's light then is illuminated by this refracted red light. And so when the deeper it goes into the umbra of the Earth's shadow, the redder it becomes, and it gets dead center inside of the umbra. It becomes this deep, deep red, and it's quite gorgeous. I've seen that a few times too. It's absolutely spectacular. So that's a bit about lunar eclipses. And I want to leave you with this really beautiful one where this was again back to October 8th of 2014 at about 5 o'clock in the morning. Hey there! Just starting in now with total solar eclipses. A solar eclipse is when the moon covers the sun, and solar eclipses are partial when only part of the sun is blocked, and total when it's all is blocked. We call them annular, not because they happen every year, annular eclipses when they make an annulus, which is a ring, or it's total, like in this image from 2017. The reason eclipses don't happen every month is because the orbital plane of the moon's orbit with respect to the Earth's orbit around the sun is tilted by about 5.2 degrees. That means that the shadow of the moon does not always come across the Earth's face at new moon. So you see on the left-hand side, that's the position of the moon for new moon if we're looking across the plane of the Earth's orbit and the moon is in exactly the same direction as the sun, except it's inclined away and up by 5 degrees. And that would be a new moon that is in the direction of the sun, but above it in the sky. And there will be no eclipse at that time. So let's see when we get eclipses. These are called eclipse seasons, and this diagram is really not to scale. There's a time of year during which the solar and lunar eclipses are possible. Lunar eclipses don't occur at every full moon, and solar eclipses don't occur at every new moon. And that's again because the moon's orbit is tilted 5 degrees with respect to the Earth's orbit. And the eclipses for total solar eclipses can only occur if the sun, moon, and Earth are in a direct line. So because of that tilt, sometimes it's above the plane of the Earth's orbit, and you're not going to get an eclipse there. Sometimes it's below the plane of the Earth's orbit, and you're not going to get an eclipse there either. But it might happen when the moon is at the node of the intersection between the ecliptic, the path that the Earth takes around the sun, and the moon's orbit around in its orbit. So those are two planes and they intersect in a line, and we call that the line of nodes. And so if the moon is new and at a node and at the ascending node, then it will be a total solar eclipse if it's exactly at that node and the node is lined up. So we have what's called a syzygy, and the syzygy is the conjunction in the sky viewed from behind, say, the moon, Earth, and sun. But this doesn't always happen. When the line of nodes is in this position, the moon might be at some other phase. It might be somewhere else. It has to be at this position, and it can be at any of these positions. And that's why it doesn't happen all the time. So this diagram is kind of deceptive because it makes it look like that the moon is always at this one place at this time. It's not. It can be, when the nodes intersect, it could be anywhere on that orbit. It just has to be at that place. Likewise, it could also be here. Actually, it happens 3 times a year because the Draconitic month, which is the month according to the line of nodes, that node line precesses with a period of about 18.6 years in the opposite direction of the moon's orbit. Therefore, the Draconitic month is faster, and therefore the line of nodes will point at the sun 3 times a year. And if the moon is exactly at new moon when the nodes are lined up, then sure, we'll get an eclipse, a total solar eclipse. So let's look at what that looks like. A total and partial solar eclipse happens when the shadow of the moon lands on the Earth. The black spot is the only place on Earth where you will see a total eclipse. The gray spot is where you'll see a partial eclipse. So it's the dark gray triangle that's going to cast is called the umbra, and that is the darkest spot in the moon shadow where the sun, if you're anywhere in the umbra, the sun is completely covered if you're behind the moon. But if you're in the larger gray triangle, you're in the penumbra, which is wider, and the sun is partially covered. The other thing that it can be is an annular eclipse. And again, annular eclipses do not mean that they happen every year annually. It means that it is an annulus. An annulus is another name for a round ring. Annular eclipses are a special form of partial eclipse where the moon is too far away to fully cover the sun. Wait a second, how is this happening? That's because the moon's orbit is elliptical, and so sometimes it's farther and sometimes it's nearer. So the moon has to be at its closest point in its orbit in order to have a total solar eclipse. If it's at its farthest point in its orbit, then it will be an annular eclipse. So we have kind of 3 regions. Again, the umbra is the darkest triangle, and so if you have a spacecraft and you're out in space and you're right in there, yeah, you're going to see an eclipse. The whitish triangle is where the 2 penumbral triangles merge, and it's not fully covered. All of these things are penumbral eclipses. It's just a really special form of the penumbral eclipse, where the sun is partially covered, but the moon makes a very large spot that almost covers the entire sun. Next, we have the shape of the shadows on the sizes of the Earth. If the moon is pointing straight overhead, there will be a pure circle. But because the Earth is a sphere, and it's not flat, it's because it's a sphere, the shape of the shadow of the moon will be spread out across a spherical surface, and so it won't be a circle, it will be an oval. So yet another way we can determine that the Earth is a sphere. Take that, flat earthers. Let's look at some future eclipse tracks. The 2033 one is only in Alaska. The 2044 one is in northern Canada, so you're gonna have to take a trip. And unfortunately, for people who wish to see that one, it'll probably be cloudy. That's usually how that flies. Just have to wait till 2045, 20 more years from the time of this recording, 21 years, to get another one that'll pass straight across the United States. And if you must go even further and you're a little person when you're hearing this, a tiny baby boy or baby girl, then you may get to see these much farther in the future. And in this deep, deep, deep future, I believe in 2099 is the farthest one out that will pass across there. So the United States will get a bunch in the coming times, but you may have to wait a very long time to see them if you don't wish to leave the continental United States and North America. But let's see what's happening in the rest of the world. In the rest of the world, we have a lot of upcoming eclipses. In this diagram, the red ones are annular and the blue ones are total. And if we see the August 2nd of 2027 going straight across the middle there from kind of going from an up to down, it first goes through the Straits of Gibraltar and then passes across northern Africa and down through, I believe that's going through Egypt and Cairo, which is amazing. So that would be great. So there will be some amazing pictures of the eclipses from the eclipse, possibly from the pyramids way out there in the Egyptian desert. And there'll also be some beautiful, beautiful images coming in from the Straits of Gibraltar in Spain. And then there's also one that kind of goes lower to up. That's in March 20th, 2034. That'll be going across Central Africa and going across the hottest parts of the Saudi desert and into Iran and into Afghanistan before it gets to Western China. That'll be amazing. So perhaps that's something other people will see. Maybe you get a chance to see it. Take a flight. Next, let's go across and notice something truly fascinating. 2028, 2030, 2037, and 2038, Australia gets 4 eclipses in 10 years. Wow, that's going to be amazing for them. And November 25th, South Africa gets it as well, but amazing that Australia gets 4 in the coming decade. So in the next 14 years from the time of this recording, you'll be able to see that. And the most amazing, I think the best one of all is, of course, December 26, 2038. It'll be the day after Christmas, so that'll be fun for them. But if you wish to, you can also take in 2039, go a little bit further south and go into Antarctica to see that total solar eclipse in Antarctica. That would be amazing. And now if we go back north, we would see in August 12th of 2026, you go to the North Pole to see that one. Or you can see it from Spain, again from Spain. Amazing, good stuff for them. And then it goes through Iceland. So that might be an amazing time to go see that and take a trip to Iceland or even Greenland. See how it goes all the way through Greenland? September 2nd of 2035, it goes through central China, North Korea, and Japan. So that will be some amazing times. Be a great time to be in Japan. Then we go back over to North America and we see, of course, in 2033, that's the one in Western Alaska. And again, the one in April 8th of 2024 coming up really soon. So there's a bunch that'll happen between 2021 and 2040. And those are all those previous maps were given by, were created by Fred Aspanak for Goddard Space Flight Center. And so this is just some amazing stuff that Fred has been doing over the years. And he's a real eclipse chaser. Make sure you get a chance to see it. You gotta plan for it. They're amazing times. Why? Because you see this. Here's an image that from Glendo, Wyoming on August 21st, 2017, taken by Vishnu Reddy. And Vishnu was standing right behind me in Glendo, and so he offered to give me these images. So this was an amazing set of images, and here they are. Again, this is during totality, and you see in a photographic image like this the corona of the sun, which we talk about what the corona is in my module about the sun. But this is what it really looks like through a camera. But it looks different naked eye. You shouldn't look at it naked eye. You should always have some sort of protection. But you do see the corona in the sky, which is amazing. That's just astonishing. It does get dark when it goes to totality. It's absolutely beautiful. I'll be showing you this in just a second. So again, a total solar eclipse is when the lights from the sun, the disk of the sun is completely blocked by the moon. And it is interesting that the moon's size is exactly the same as the sun's size in the sky, and we'll get to why that is later. So an annular solar eclipse, here was the one that just happened on October 14th of 2023. And this is by JAXA and NASA and was taken by the solar telescope Hinode as the moon came between it and the sun. And so this is from science.nasa.gov, so go there and look for this image from JAXA and NASA. Next, this was taken in National Park Service by Kevin Dostaxler, October 14th from the desert Southwest. And this is a progression of all the images taken in together. And this is the umbral shadow is seen from space. And this is a really interesting thing. And I believe this was aboard the International Space Station on November 13th of 2003. And this was downloaded from NASA's Goddard Space Flight Center. When you go see an eclipse, solar eclipse, make sure you do it safely. First, look over on the left-hand side, get yourself those eclipse goggles. You need that, or else you're gonna, you'll damage your eyes. The sun is really bright, and just because the moon's covering it doesn't mean that it can't damage your eyes. And it's really wonderful to watch the moon go across the sun. And if you have these kind of glasses, you will be able to see the chunk taken out as it happens. Also, if you're really smart, you can put a solar filter on top of a little junky telescope that you don't mind burning the interior optics of and projecting it to the side so people can watch it without having to look through little glasses. Or you can make a pinhole telescope, like that diagram. It basically is a cardboard shield with a little pinhole, and you typically want to make that pinhole out of foil, so it's a very tight pinhole. It's better if you put it inside some sort of box in that thing. Like the kids in the middle, they won't see the corona. But you would see the corona if you put the pinhole camera inside a box and then look inside the box from the side. At the very minimum, if you're going to go see a solar eclipse, get some eclipse shades. Now let's take a look at some images that occurred during the August 21st, 2017 total solar eclipse that I went to in Glendo, Wyoming. We were all situated outside of a football field in a small high school, and it took a long time to get there, and it was a big trip that was associated with a wonderful travel agency that I worked with. But I met a lot of nice people on the way. In any event, these images were taken by a person that I met there, Vishnu Reddy. This started at the first contact, is what this is called, when the disk of the moon starts to occult the sun. That is called first contact, and that is roughly at about 10:24 in the morning at the time at Glendo, Wyoming at the time. The sequence up to totality took about an hour and 22 minutes for the moon to move across the sun. So let's see how long this took and watch the progression of images that occurred one after the other, all the way up to totality. I paused it here because look at those things. They're called Bailey's beads, and the beading is because the moon is not perfectly round. It has very tall mountains. So what we're looking at is sunlight that's coming through the between the mountains. And that's why there's a little gap in there, and there's some little darker spots. It's because there are tall mountains that are cutting off the sun as it's on the moon, as it's passing in front. We also start to see this pinkish glow that I'll describe in a little bit later. And now we get closer and closer to totality, and finally here we are at totality at roughly 11:42 in the morning. This presence of totality lasted about 2 minutes and 29 seconds. Only 2.5 minutes of totality. So everybody was like staring and ooh ah. It's just amazing because you can see this in the sky. You will see the corona using the using the special not glasses as per se, but just a filter, a solar filter that allows you to look straight at the sun. You see off to the side on about almost 3 o'clock, maybe 2:30 on the sun and 4 o'clock on the sun, those little pinkish loops. Those are prominences. Prominences are huge loops of gas, of hydrogen gas. That's why they're pink. And I discussed this in the video on the sun. Those things are huge. By huge, I mean each of those little tiny pink loops is much bigger than the entire planet Earth. But the more prominent thing you see is called the corona, which are all these wispy, gaseous elements that they're streaming away from the sun. They're extraordinarily hot. The surface of the sun is about 6,000 degrees Kelvin, but the corona is millions of degrees Kelvin. And so they glow by the heat. They're so incredibly hot that they glow mostly in X-rays, but we see them in visible light as well as atomic transitions in the visible light region. So this is a solar wind, and these particles are being ejected from the sun at extraordinarily high speeds. And I invite you to go look at my video on the sun. What's really important in here is that we get 2 minutes and 29 seconds of totality in Glendale, Wyoming, and you do see this in the sky. This is a photograph, but you also see it in the sky, and you can see it with those glasses. It's just an amazing view. So let's continue on. And then we get to this fascinating part where the sun is just coming out from behind the moon, and we see more of the pink chromosphere of the sun. We see more of that tall prominence at about 2:30 or almost 3 o'clock on the sun's face. And we're reducing the amount of the corona that we can see simply because the corona is very dim with respect to even the chromosphere. So as it came out from behind the moon, or more specifically, as the moon went on its merry way on its orbit, the sun's now reappearing. So the sun keeps appearing more and more and more. We see the beads again, and then finally there's the Bailey's beads again on the other side of the moon. We see that there's one tall mountain in there that's blocking it completely, but then we are still able to see the chromosphere, the pink chromosphere. And this is a great image because you have the chromosphere and the growing photosphere of the sun, which is the bright spot. That would be the photosphere of the sun, but we're still able to catch just a bit of the chromosphere in the same image, which is an amazing image, actually. So this is right after 11:45 in the morning, and by 1 o'clock in the afternoon, 1:09 in the afternoon, the moon will have passed completely across the face of the sun, ending the entire eclipse event. It was an amazing event. There is no question. I would do it again, and I'm planning to do it again for the 2024 one. And I'm going to try to do them again later in coming decades and go to other countries. It's just an amazing experience. And if you do not get the chance to see a total solar eclipse in your lifetime, you've missed out. It's an amazing experience, and you should really try to get in the path of totality. Not just see a partial, get in the path of totality. It's a very narrow band, but you gotta try to do it. It might cost you a bit, it's gonna be very expensive, and it only lasts for like a couple of minutes, but it's an astonishing feeling that you get. There's this primal sense, and I'll show you why in a second. Vishnu Reddy collected this data, and this is a fascinating set of data. It shows the temperature of the air. The temperature really does drop. It dropped almost 25 degrees between the first contact and during totality, which is those 2 orange bars in the middle. That's totality. It takes a moment for the atmosphere to catch up, but yeah, it dropped in temperature, and you could feel it. You did want to put on a coat as time went on. You did want to put on a sweater, but nobody dared do that because it was going to last for such a short period of time. You didn't want to miss any of the action that was happening, but it was amazing to actually to feel the temperature difference. So what did it look like at Glendale, Wyoming during totality, in the path of totality? This picture, again, also by Vishnu Reddy, is about halfway to totality. And we see that it actually does kind of look dimmer. The grass has a different hue to it, as well as
you start to see a purplish hue to the sky, and that is true. You do start to see that dimmer thing. It's like you have a sunset, but the sunset is in the sky. That's what it feels like, and it's very strange. You have a sunset happening in the sky. That's the only way to describe it. And it's very strange. Birds start to go to sleep. They really do. They think it's sunset. It's amazing what happens during totality. Let me just show you a series of images that go from that moment, about halfway through totality, all the way through totality. Here it is, totality. This is what it looks like in totality. You're in full darkness. You're in the shadow of the sun, and you're ringed by a sunset. Very strange. The sunset is all around you in every direction because you're in the middle of a shadow. And yeah, you do see, I believe that's planet Venus up there. That's what that white dot is. That's not a marker on the image. That's Venus in the sky. You do see that. Stars come out. You can see stars. It's absolutely amazing. And it was an incredibly special time for me for another reason. My parents are seated here. So I'm off to the left, and my mother is in the middle, and my father's to the right, and he's got a balloon in the background. It was great. These balloonists were trying to keep up with the shadow. It was wonderful to watch them scoot across the horizon as they tried to race the shadow. I do not know how they did that, but they were having a great old time. And this was an amazing thing because my father did pass away in 2021, so he passed away 4 years later. And this was such an amazing opportunity for me to be able to take them on this tour of Wyoming and Colorado. My father had been the president of Northwest Community College in Powell, Wyoming. So Glendo was familiar territory to him, and he was a man of the Southwest. He grew up in Arizona, and he loved all that stuff. So the desert Southwest was part of the family. And I was out there also doing, covering the eclipse for WNYC and 1010 Winds and AM New York. And I gave a live broadcast, a couple of interviews with Salon. It was just an amazing time. I was trying to give a live broadcast to 1010 Winds Radio right during my intention was to be able to broadcast what it was like inside of totality. But unfortunately, it was just so sad. My battery ran out like 10 minutes before totality. So there I was, just standing, enjoying it for myself and not giving it to viewers. But it was an amazing, amazing time. I had a wonderful time with that, and it was completely special to be able to take my parents with me, and it was great. Besides, this for them was also wonderful as well, because part of the tour that I just described at the beginning of this was that it went through Trail Ridge Road in Estes Park, Colorado. And the last time they'd been on that road, they were driving from Boston to Los Angeles in 1955. He was 20 and she was 18. And can you tell? Can you tell there's a bit of a wonderful memory that's going on there? It was incredibly special to be able to take them with me on this wonderful, wonderful tour. Well, after it was all done, we tried to get home from Glendo back to Cheyenne to our hotel, and this happened. There were so many cars that it took hours to get back. I think it took. We stayed at the football field until totality was complete, and I think we packed up pretty quickly. I seem to remember we kind of got on the road about 1:30 or so, and the bus driver really wanted to get us going, but we didn't get back to the hotel till 6 p.m. or 7. It took a long time. And there were a couple of people that thought they'd be funny and ride on the grass to go south and get off the highway, but state troopers weren't having any of that. And got people back on the road. I was really surprised they didn't close the northbound road over there and get people off these highways as fast as possible. But there weren't any incidents of note. There was that guy who did run out of whose radiator did overheat, and there was a really big problem in Wyoming with gasoline, and they ran out of gas, I believe, in a lot of gas stations across Wyoming. So when you do go to see a total solar eclipse anywhere, you have to be prepared for running out of gas in your car because everybody and their cat, their dog, their hamster is going to go, and they will use up all the gasoline there. So perhaps an electric car with a solar panel would be a really good idea with this time. Do be prepared for anything if you do go to a total solar eclipse. And so that was an amazing view, and here again is the corona around the sun during totality, that 2.5 minutes of totality on August 21st, 2017. Now let's look at why the moon has exactly the same angular size in the sky that the sun does. That means that the moon exactly covers the sun during a total solar eclipse. People think this is kind of weird and it must have some basis in something, or like double rainbow, what does it mean, and all that kind of stuff. But what it really means is a confluence of factors that began with how the moon was formed, the fact that the moon is tidally locked to the Earth, and that the moon's orbit has changed over time. So let's look at all of those things, because right now we know from Apollo missions, the mirrors left on the moon, that the moon is drifting away about 1.5 inches further every year. That's really interesting. So let's look at what this all means and how it relates to why it's the same size. So let's start with the formation of the moon. The giant impact hypothesis, which is depicted here, suggests that the moon was formed from the ejecta of some collision between the early Earth and some Mars-sized planet approximately 4.5 billion years ago. And that would be roughly about 20 to 100 million years after the solar system formed. The object that hit the Earth so long ago has been informally named Theia. Why? Because in ancient Greek mythology, Theia is one of the 12 Titans, who are the children of the earth goddess Gaia and the sky god Uranus. Her brother consort, and this is kind of what the thing that kind of makes people go about it, is Hyperion, a titan also, and a god of the sun. And together they're the parents of the sun, the moon, and the dawn, Helios, Selene, and Eos. And Hyperion is, just like Theia, hardly ever comes up in the mythology of the Greeks, and Theia is mostly important for the children that she bore, Selene, Eos, and Helios. That just means that the only thing you ever really hear about her is that she's at least the goddess of sight and vision, and had endowed gold, silver, and gems with their brilliance and value. Which is actually pretty interesting, considering that when a massive collision like this occurred, the heavy elements such as gold and silver sank to the center of the Earth, and very few of them went into the moon. Anyway, so this giant impact hypothesis is currently the favored hypothesis for the formation of the moon, and there's a lot of evidence that supports this hypothesis. The first is the moon's orbit has the same orientation as a similar orientation to the Earth's spin. The Earth's rotation axis and the moon's orbital axis are very closely aligned. They only differ by a little bit. The moon and Earth system also contains a huge amount of angular momentum. And this angular momentum is tied up in the Earth's rotation, the moon's rotation, and the moon revolving around the Earth. This is the sum of these things is significantly higher than the other terrestrial planets, Mercury, Venus, and Mars. And a giant impact would have definitively supplied this excess momentum, or it could have. The moon has a small iron core, and this gives the moon a lower density overall than the Earth, and computer models show that a giant impact of a Mars-sized body with the Earth would seem to make the impactor's core penetrate all the way into the Earth and fuse with the Earth's core. That would leave the moon, which was formed from the ejecta that we see here, that would be from the surface level stuff, like the less metallic iron, because the Earth at this time had already partly stratified, meaning iron had sunk to the core, and less heavy materials were at the surface, such as silicates and so on. Furthermore, there is evidence from star systems other than the solar system where we see evidence of collisions that would result in debris disks. Here we see one of the earliest that was ever found. This is the star Beta Pictoris. Beta Pictoris is in the dead center of this image. There's an exoplanet, Beta Pictoris b. That blue occultation image is because that's an image from the Very Large Array. But the infrared image goes up and to the left and down and to the right. That's European Southern Observatory Adonis instrument. But what we're really caring about there is not the exoplanet in the center, which is really cool, but really the dusty disk that is occurring in the upper left and lower right that surrounds the star Beta Pictoris. Debris disks would occur if there were major impacts, and giant collisions are very much consistent with the leading theory of the formation of the solar system, and such debris disks are found around other stars, so we do believe that this is the case. Next, the Apollo moon samples showed that stable isotope ratios of the lunar and terrestrial rocks, the rocks from the moon and the rocks from the Earth, they're identical, and that implies a common origin. Also, the Apollo moon samples indicate that the moon was once molten to a great depth, and this would have required a huge amount of energy than would be predicted from available if you just had an accretion of the body from the moon size. It came together under gravity inside its own dust, inside that dusty disk that we saw around Beta Pictoris. Now, in order to make it much more molten quite deeply, an extremely energetic process, such as a giant impact, could provide that energy. Next, the moon is depleted of volatile elements compared to the Earth. Volatile elements vaporize at comparatively low temperatures, and they'd be lost in some high energy event. With the moon's smaller gravity, would not be able to recapture them, but the Earth would. That means you need to have some extraordinarily hot environment, and an impact would provide that. And this image is from December 13th of 1972, and this is Harrison Schmitt from Apollo 17 taking such lunar samples during their second extravehicular activity on the moon. So yes, the moon was actually visited by people. Isn't that wonderful? Let's assume that it has been, that the moon was created in a giant impact. Fantastic. Now that means that the moon and the Earth are orbiting each other, and they pull each other gravitationally. And as they pull each other, they orbit each other, but there's also, because they're going around in little circles around the center of mass, actually more like an ellipse, but let's keep it a circle for ease here. As they go around that center of mass, as we just showed, the red arrows, so we have these two dots, the moon would be on the bigger circle because it's swinging around, and the Earth would be on the smaller circle because it's the more massive body, so it would be closer to the center of mass. The gravitational attraction between them would be the same, and that's the red arrow and the green arrow. And the centrifugal acceleration, so gravitational acceleration is red, the centrifugal acceleration is green. And these things are balanced in this system. Otherwise, if they weren't balanced, then they would be either be falling together or flying apart. And part of that centrifugal acceleration, in fact, the centrifugal acceleration, is due to the fact that they're orbiting a center of mass. If they were not orbiting a center of mass, there would be no centrifugal acceleration. So that's what the white arrows were indicating, and that's what I showed with this thing before. So the X marks the spot of the center of mass. And so now when we've seen that, we can say, fine, we have actually not just point masses, but they're distributed objects. And this is an important thing. So now we've got a big Earth on the left and a smaller moon on the right. Remember again that in a rotating reference frame, we have to remember this is a rotating reference frame. I'm not going to show that rotation from this point onward, but I wanted to show you that from that diagram before that we're really acting in a rotating reference frame, and we have to take care of both the gravitational acceleration red and the green centrifugal acceleration, which is due solely to the fact that they're in a rotating reference frame. So we've done this. Let's remove the orbital parameters and separate out those white arrows just so we have clarity, so we know what we're looking at. And now that we're in the rotating reference frame, rotating along with the moon and Earth as they go around their orbit, that center of mass, we then say the next thing, which is, what's it like when we isolate just the surface bits when we want to see the effect of the moon on the surface bits of the Earth? Strictly speaking, because we're looking at centers of mass, we really should be looking at every little bit of the Earth, from the nearest to the farthest, all the way through the core, everywhere in the entire Earth. But that would make a really messy diagram, and I don't want to do that. I want to actually be clear, so I'm just going to look at the surface bits. But we have to remember that the tidal interaction from the moon on the Earth is going to be due to all of the parts of it. But I'm just going to choose a series of lines. But first, what I'm going to do is say for each of those lines is affected by the same centrifugal acceleration. And this is true if we ignore the Earth's rotation. This is a good approximation if we ignore the Earth's rotation. If we added in the Earth's rotation, then we would just have some flattening of the Earth that we would have to take care of. But really, we think about the experience of centrifugal acceleration at that point in that rotating reference frame. So what do we mean? They're always pointing in the same direction. So I just want to help you with that. What I mean, why I can say that all of these green arrows are the same. It's because in a rotating reference frame, they're all going to rotate around their own center of mass. So let's see what that kind of looks like. Each of those green arrows is staying with respect to each other as they orbit the center of mass. When you have a distributed system that's orbiting that does not rotate, each point is rotating around its own circle in order to maintain the non-rotation of the Earth. And that's what we just saw. So those red arrows showed that the green arrows, these red arrows, which are not gravitational, these red arrows show the difference between the center of mass for the surface bit and the center of mass of the entire system. And they're the same because they're going around a circle that has the same diameter at the same speed. The centrifugal acceleration field that is experienced at the surface of the Earth due to the rotating reference frame can be shown to be the same for every point on Earth in diagrams such as these. Let's get back to this original thing where we have centrifugal acceleration inside this rotating reference frame. And now what we're going to do is we have to take the center of mass, the red arrow in the Earth, and apply each of its bits per bit. So that's what we're going to do next. So what I did is I removed the center of mass of the Earth and put the yellow arrows on each of the lines that says each bit of the Earth here is feeling a gravitational acceleration towards the center of mass of the moon over on the right. And so we have two arrows at each point, one centrifugal, which is green, and one gravitational acceleration, which is yellow. The yellow ones differ from the green ones because some points on Earth in this distribution are closer to the moon and some are farther. If they're farther, the arrow will be shorter. If they're nearer, the arrow will be larger. If they're off axis, they'll have to point towards it, so they'll kind of swing down a little bit. And so if like at the very top, the yellow arrow is bent very much down compared to the green arrow. But in the near side, at like say 3 o'clock, the yellow arrow is exactly the opposite direction as the green arrow, but it's longer, so therefore the gravitational acceleration is greater. But at 9 o'clock, the centrifugal acceleration is greater than the gravitational acceleration. All of these things added together would make the red arrow we saw on the previous slide. Okay, so let's get rid of the lines just to make it a little easier to see. Now I'm going to add the two arrows together. If I vector added the green and the yellow one together, I get the little blue ones. And these are the net acceleration inside of this rotating reference frame at that point on the surface of Earth. So this is a vector addition. So the green arrow plus the yellow arrow equals the blue arrow for each one of them. This is vector addition. And so we're left with these. We really don't have the other two things because their net effect is the blue arrow. And now let's look at all of the arrows on that surface, every single one. And now let's dim things down so we can see it a little easier. And now we're left with the familiar tidal bulges. They arise because of the differential gravitational field between the moon and the Earth inside of a freely falling two-body system in a rotating reference frame. That's important enough to say it again. The tidal bulges arise from the differential gravitational field between the Earth and the Moon, where you look at the points on the surface of Earth and every point on Earth as it's getting pulled on the Moon compared to its centrifugal acceleration away from the center of mass inside this freely falling two-body system in a rotating reference frame. These tidal bulges would not happen if the Moon and Earth were not orbiting each other. They simply would not happen. So now let's draw a line between their centers of mass to get some sort of distance indicator. And now let's remember that the Earth is actually rotating. And because the Earth is actually rotating, this rotation drags the oceans ahead of the true line between the centers of mass. So that tidal bulge is not pointed always at the Moon. It's ahead of that. And why? Because the Earth is rotating faster than the Moon is orbiting. So when that happens, the friction between the Earth and the oceans drags that forward. The flexing of the Earth is not really too huge, but the oceans are the significant thing that is taken into account. But that wave takes time to process, and the rotation drags it forward very quickly, so that bulge points off axis. As a result of this misalignment of these two lines, that creates a torque. And that torque imparts angular momentum into the Moon's orbit, which speeds it up, and therefore it falls away from the Earth and it grows distance with time. And the Earth's rotation slows. Let's say that again. The reason that the Moon's orbit is changing is because there's a torque between the line of the bulges of the tides that's dragged forward by the Earth's rotation compared to the center of mass between the Earth and Moon. And that creates a torque, and that torque slows down the Earth and speeds up the Moon and makes the Moon drift away. And over time, this happens. It gets farther and farther away. After its formation, when the Moon was formed, it was very, very, very close. It might have been, say, 15,000 miles away or so. Only a few Earth radii away from the surface of the Earth. And today, as a result of this tidal interaction, 4.5 billion years later, they're now separated by 240,000 miles, which is about 385,000 kilometers. And the Earth is spinning slower, much slower than the time of the Moon's formation, and the Moon is much further away than the time of the Moon's formation. And the Moon took a very short period of time to tidally slow down to have the same rotation period as its orbital period. That happened inside of 4.5 billion years for the Moon, because the Moon's a smaller body. And so the torque that it would have had on due its rotation, and that would have back reacted, of course, on the Earth as well, that would have spun, that would also serve to push them apart. So the Moon now faces the same way as the Earth. I just ignored everything that I did with the Earth. I ignored that for the Moon for this diagram. But it did happen on the Moon as well. And that's why we see only one side of the Moon. So due to tidal acceleration, therefore, the orbit of the Moon becomes about 3.8 centimeters more distant every year. And that's about the same rate that your fingernails grow. That also means that the average solar day, which is defined to be 86,400 equal seconds, is getting longer by 2.4 milliseconds per century when measured in standard SI units with respect to atomic clocks. So the atomic clock second is different than the mean solar day second, and by 2.4 milliseconds per century. This small difference accumulates over time and has accumulated to the point where in 1972 the world adopted the leap second in order to compensate for differences in this time base for these two standardizations. Thinking about the Earth's rotational slowdown, how long will that take? Well, we can predict what it'll be and how far away it'll be. Eventually, the Earth will slow down until the rotational period of the Earth is 47 Earth days, and at that time, the Earth would face, only one side would ever see the Moon. Just the same way if you're on the Moon, only one side can see the Earth. But models that predict this predict that it'll take about 50 billion years. 50, not 5, not 15, 50 billion years to achieve that. That's too slow. That's really too slow, because in a 1.5 or about a billion years from now, really in a billion and a half years from now, the sun, whose radiation is increasing, and it will increase to the point where water will not be able to exist on the surface of Earth, and all the Earth's oceans will boil away. That'll reduce the tidal interaction. But even without this slowdown cannot be completed in 4.5 billion years, which is when the sun is expected to grow into a red giant, destroy the Earth and moon. So the Earth will never, ever, ever get to that point, and the sun will die before the Earth slows down to that point. So let's see what that looks like in a separate diagram. So right now, the Earth is about, well, right now, the Earth is about 8,000 miles wide, about 12,700 kilometers. And let's see how that looks with respect to the moon's orbit. The moon is about 2,000 miles across, or about 3,500 kilometers, and its distance is about 385,000 kilometers. So there's the current moon orbit. The current moon orbit is about 240,000 miles. It's really tiny compared to the other orbit, and that's why we don't see lunar and solar eclipses all the time, because it's far, and it's a very tiny target. But at this distance from the Earth to the moon, that means that the moon, given that the moon is 2,150 miles across and about 240,000 miles away, that means the moon is about 0.5 degree in the sky. Now the sun is very, very large, and it's 150 million kilometers away. So therefore, it's about 0.5 degree in the sky. That's the current orbit. It's just grown to that place. In earlier times, the moon would have been larger. How much larger? Here we go. At the time of the moon's formation, 4.5 billion years ago, the distance would have only been about 24,000 kilometers, or about just under 4 Earth radii away. That's really close, 15,000 miles away. That's super close. At that distance, when the moon was formed, it was about 8.5 degrees in the sky, or 8.3 degrees in the sky. This is enormously close. Now, the Earth was spinning a lot faster, and the moon was going around quickly, and the month was a lot shorter. This was a whole ball of wax. It was a really crazy time. And well, after the formation, the Earth did not look like this. It just was a hot, glowing, molten thing, and so was the moon. But let's see what that might have looked like. Let's pretend. So let's go today. Here is an image that looks over Europe, taken as an AP photo by Petros Giannakouros. And in this image, we see a full moon rising in the east, and it's quite beautiful. And it's looking over a hillside in Europe. It looks absolutely gorgeous. And in this image, the moon is 1/2 degree. So whatever the size scale of this image that we're seeing, the moon is 0.5 degree. What would this image look like 4.5 billion years ago? Well, it kind of would look like this. This is really kind of scary. The moon would look this big in the sky. It would be about 16 times larger in the sky. And of course, this is Photoshopped. Of course, this is not a real image of the moon. I've just Photoshopped this. I even made the background look terrible just to make it so it's obvious it's Photoshopped. Anyway, when the moon was this close, there would be no annular eclipses because the moon is much bigger in the sky than the sun. The sun would still be 0.5 degree in the sky, but now the moon is 8.5 degrees in the sky. It's huge. There would also likely be very few full moons that weren't in partial eclipse. There will always be a full moon, but when it's in full moon, there would always be a partial eclipse. Why? Because the moon's orbit is inclined only 5 degrees with respect to the Earth's orbit around the sun, but the angular size of the moon is 8 degrees. So at the farthest it could be is 1 degree outside of dead center, and the Earth's shadow is still pretty big. So we would always see 4.5 billion years ago some sort of partially lunar eclipse. And you would almost always get solar eclipses, where the moon would go in front of the sun and completely block out the light to the Earth. That's amazing. That would happen all the time. Eclipses back at the moon's formation, total solar eclipses would happen all the time. But you wouldn't see the corona like we do. Why? Because it's 8 degrees in the sky, and the sun is a half a degree in the sky, and the corona only makes it at most a degree in the sky. So this combination of the moon moving about 1.5 inches further every year led us to be able to have eclipses. All the kinds of diversity of eclipses that we know it's a temporary phenomenon. Now, we've always had them. They've always been solar eclipses, but the moon's angular size has been shrinking over time. And during human evolution, during the time of Homo sapiens on Earth, the moon's size has been roughly this. So many of the archaeoastronomy sites have been found across the world, many of them are World Heritage sites. They describe how ancient cultures were really trying to understand the motion of the sun and the moon. Hundreds of millions of years in the past, the moon was closer, and therefore larger, so every total solar eclipse, well, it was either total or partial, and there were no annular eclipses. That would be hundreds of millions of years in the past. Due to this tidal acceleration, we now have annular eclipses because sometimes the moon is closer in its orbit and sometimes further. And millions of years in the future, the moon will be too far away to finally completely cover the sun, and there will no longer be total solar eclipses. And in that same time frame, though, the sun is going to become brighter, and so it'll appear to be larger in size. And when will this happen? When will we get the last eclipse? The estimates are somewhere between 650 million and 1.5 billion years in the future. That's going to happen way long time in the future. So there's nothing to say, oh my goodness, humanity is going to see the last of this. Well, if humanity manages to live to 650 million years and be that successful of a species, good on humanity, because that would be amazing. But we don't have to worry about that today. We don't have to worry about not ever seeing an eclipse. They're just relatively rare. So let's circle back to the original question that I posed at the beginning of this video. Why? Why exactly does the moon cover the sun almost perfectly during a total solar eclipse? And in fact, today it can. It can be an annular eclipse that's a little too far away, or it can be a total solar eclipse where it's closer and it totally covers the sun by more than a little bit. But is there some great cosmic significance that says that the moon is this distance and the sun is that distance and they're both the same angular size in the sky? No, you could assign some sort of purpose to it, and that's what people typically think when they think why. This video was more about how. Why? The why meaning how does this happen? How did it happen such that today we see that? It's just a confluence of events. It's not like we were put on Earth yesterday and this was created for us. No, eclipses happen for many planets in exoplanets all across the entire universe. In fact, we discover exoplanets by them passing in front of the stars and creating partial eclipses of those stars. That's how the Kepler Space Telescope found many of them, by these tiny little partial eclipses of distant stars that it can see. And so, and if you were on Jupiter, there's so many moons, you'd have all sorts of little eclipses. And so what we look at is that there's no religious significance. There's no purpose for a total solar eclipse. So when we say why exactly? Well, it's just that time in geologic history where it is doing that. It won't do that in the distant future, and it was slightly different in the past. It's just that the moon is slowly moving away, and as it does so, it gets smaller and smaller and smaller in the sky because its angular size is getting smaller and smaller in the sky. That's what we mean. It's physically not getting smaller. It's just moving away, so it looks smaller. That's why. That's all. It's not super significant in that way. However, it is emotionally significant. It is a beautiful thing. And if you do get a chance to go see a total solar eclipse, you must go see one. It's really exciting to see the stars come out, to see the ring of sunset all around you. And I wouldn't trade it for the world. I went to Glendale, Wyoming, and this is a picture of me with my parents. And it's just an amazing thing. I would not trade it for anything. And in fact, you should make sure you get in there too, because the visceral feeling that you get during that is so significant that I can't imagine that these events did not have significant impact on human feelings and evolution over the last tens of millions of years. Maybe even, and I'm just speculating here, totally speculating, that solar eclipses had an influence on our thinking with respect to religion and the bases for it and why there's lunar calendars throughout many religions. It could just be that that solar eclipses were such significant events that they helped create the need for cosmology, the needs for religion. Amazing. But that's total speculation, and I'm sure there'd be a lot of people who would really disagree with me on this, and that's okay. I'm not holding fast to that idea. Let's look at planetary motions as they appear in the sky from the Earth. I've taken a still of a simulation that I'm going to show you shortly. Across the bottom is the horizon with the cardinal directions marked south, southwest, and west. So this is a very wide angle view. Also, if you look at the time in the upper corner, we see the date is very far in the future in 2044, sometime in May. And the time at night for this point in the simulation is approximately 10:40 p.m. local time. You also see Mars highlighted with the red targets as well as its name. We also see an orange line that surrounds Mars, and that orange line is the path in the sky that Mars has taken or will take, and I'll show you this. So in this simulation, we're going to start very much before this time in May of 2044. We're also going to start much later in the evening, or actually, if you consider it, far earlier in the morning. And at some point, I'm going to pull it back to late in the evening like this so we can see it. This way, we can see over the course of many, many, many days and weeks how Mars changes its place in the sky with respect to the background stars. The grid is the equatorial grid, which is a coordinate system that's fixed with respect to the background stars. And the track that you see, that orange track, is the path that Mars took in the sky to get to this place. So now what we'll do is we'll look at this exact simulation and see what we get. Okay, so now I've booted up the simulation. We see it's approximately 5:40 in the morning, way back in October of 2043. So this simulation takes place over a very large period of time. And we see Mars is tracking out this point in its orbit that makes that orange line. And there's the retrograde motion. That retrograde motion is when it stops going from west to east and starts going from east to west. You can see that the motion is towards the western horizon. And as time goes on, the retrograde motion halts, and we're done. We're back to prograde motion. Just want to point out with a still from this clip the following things. Again, we have the horizon there. We've got the equatorial grid showing us a map of the background stars. We have the moon sitting over there, zipping through this entire simulation as we saw it. And then we have the orange trail. The orange trail has the faded part where it used to be, and the most recent part is where it's brightest, right? We see that, the tip of the tail is right by the planet Uranus. This is pretty cool. But that's where it was, say, many, many months ago. And it went along this track, prograde, meaning west towards east. And west towards east in this image is from right to left, because to the left of west is south, and further left would be east on this thing. So the prograde motion was earlier, and the retrograde motion is when it kind of turns around to the far left and makes a little curl at the top and goes back over the top. That is the retrograde motion, and then it curls back again to go prograde again. Of course, this is all due to the fact that both the Earth and Mars orbit the Sun. The Earth orbits the Sun closer than Mars. So we get the retrograde motion when the Earth is between Mars and the Sun and overtaking it. Because Earth goes faster around its orbit than Mars, it overtakes it and we get that retrograde motion. That is simply an effect of motion of the Earth, effectively lapping Mars as we go around the Sun. This is the same for all the planets. Every planet experiences this, and now we're going to go look at that too. Let's first take a look at Mercury. Right now we're seeing Mercury going, in that moment we just looked at it, from east towards west. That is retrograde motion of Mercury. Notice that it is now turned around and it's starting in this as we go forward in time, moving with respect to the background stars now west towards east. And to make it kind of a little bit easier to understand what we're doing, I'm actually toggling on and off both the atmosphere and the ground so you can see this. So one is like we're out in space and the others we're on ground and trying to actually find Mercury. Finding Mercury in the sky is always difficult because it's always close to the sun. It's never much more than 28 degrees away from the sun in the sky, and it's probably best if it's going to be at greatest elongation in the morning, in the sunrise time, that you want to do that in the fall, not the spring, and likewise you reverse that for western elongations. But here we see once again, I think I'm going to spin it back in time. Yeah, let's center it back up. As time goes on, it gets closer and closer to the sun as it's going in prograde motion. So now let's like spin it back all the way back to where it was going to start doing that retrograde motion. And now we go forward in time again from January 1st. And we can see that it's going from the east towards the west. That is its retrograde motion in the sky. And so this is with the ground turned off. That green line is, of course, the horizon. And the sun is below the horizon here. But if we turned on the atmosphere, it'd be very hard to see. And there's Mercury again going prograde, again back towards west, towards east in its prograde motion. It's always hard to find Mercury in the sky because it's so close. I've done it many times with my telescope. But it's kind of funny when people want to talk about, oh, I'm having a problem because Mercury's going retrograde. It's like most of those people probably have never even tried to find Mercury in the sky, much less know where to look for it. Now I'm going to look at Mercury, Venus, Mars, and Jupiter, all as seen from space and tracing their orbits. Let's define what we're looking at here. The red oval that seems to be going around the sun, upon which Mercury seems to be traveling, is actually Mercury's orbit. If for some reason the orbit itself was demarked by some stuff in the sky, like it was a physical object, that is what we would see. It is an ellipse that is around the sun at a very great distance. And that is the path that Mercury truly travels on. If we were to look at the solar system from above, straight down, we would see that Mercury is orbiting the sun in a counterclockwise manner on an ellipse, and that's what this red line denotes. The path marked ecliptic is the path that the sun takes in the sky over the course of the year, and that is actually the projection of the Earth's orbit around the sun projected out into space. And we're looking back at the sun, so it looks like the sun is orbiting us, but in fact we are orbiting it. The orange line that trails a planet, one of any of the planets we're looking at, is the path in the sky that the planet apparently takes with respect to the background stars. Sometimes that path is what we will call prograde, meaning going west from east. The dominant motion of all planets is prograde. The sun only marches prograde west to east, and occasionally a planet will march retrograde, meaning east to west. When it does so, it will make a backwards loop or edge or curl or something that is an eastward bound motion. The types of planets we're looking at, there are two kinds. We'll call them inferior planets and superior planets. That doesn't mean one planet is better than another planet. What it simply means is that if they are interior to Earth's orbit around the Sun, then they're called inferior, and those are Mercury and Venus. The superior planets are Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, etc., which are exterior to, which have orbital radii that are greater than Earth's radius. Once again, inferior is smaller orbital radius than Earth's, superior is greater than. Therefore, when we get retrograde motions for, say, Mars's retrograde motion when it happens at opposition. At opposition, it is at the exact opposite place in the sky from the Sun. For inferior planets, retrograde motion is at conjunction, or inferior conjunction, meaning Mercury or Venus is between the Earth and the Sun, and that's when we get that particular kind of retrograde motion. The blue grid is the equatorial grid of right ascension and declination. That is one of the ways that we have a fixed grid of coordinates with respect to the background sky. That is the coordinate system of the stars. The Sun and the planets all move with respect to that. You'll also notice that the orbits tend to go up and down and wag back and forth, and these tilts happen. That's because we're looking at it from an equatorial coordinate system. The equatorial coordinate system has as its north celestial pole straight up from the Earth's north pole. That does not correspond to the Earth's orbital axis. If it did, then this red line that we see here, or the ecliptic, would be flat with respect to the, or at least flat with respect to the celestial grid coordinates that we see in the background. But the Earth's rotational axis is tilted 23.5 degrees with respect to its orbital inclination. Therefore, that grid, and that's where we get this tilt back and forth, it kind of looks wobbly. The moon is also making an appearance consistently through this entire simulation as it scoots across the sky once a month. And so it's a bit of a bother, because there it goes, because we're trying to actually look at the planets. But if we were considering it from ancient times, the moon was considered one of the classical planets. It always goes prograde, just like the Sun. It does not do retrograde motion. Remember, retrograde motion is due to the fact that all the other planets orbit the Sun. Some orbit nearer to the Sun, and some orbit farther from the Sun. So let's summarize how these motions occur. As Mercury, Mars, and Earth go around the Sun, when Mercury is between the elongations going through inferior conjunction, then we will get retrograde motion of Mercury. And when we have Mars going from between the quadratures through opposition, then we get retrograde motion of Mars. Notice that this is seen from above, and if we were looking from above, we've generalized it to circles. We know they're ellipses because of Kepler's laws and so forth, but we're making this easier to see. When we look from above, they're orbiting in ellipses, or in this case circles, just to make it easier to see. And we get the fact that the reason that the retrograde motion occurs is because Earth is simply going slower than Mercury and faster than Mars in its orbit. Kepler's laws state that the farther something away is, the slower it's going in its orbit. And all this summarizes together to show that the retrograde motion is simply due to Mercury passing or lapping Earth, or Earth lapping Mars. That's where it all arises from.